What if our universe is just a tiny part of a much greater reality? The observable universe spans about 38 billion light-years, filled with countless galaxies, stars, and cosmic wonders. Yet, its true limits remain unknown. As we explore further, we can't help but wonder, what exists beyond what we can see? Are there boundaries where our understanding of physics breaks down, or entirely different dimensions waiting to be discovered? The observable universe is a vast expanse that represents all the celestial objects we can potentially see, limited by the speed of light and the age of the cosmos. Spanning about 13.8 billion years, its reach is determined by how far light has traveled since the Big Bang. Think of light as a messenger from distant stars and galaxies, revealing their existence to us across unimaginable distances. Determining the boundaries of the observable universe involves understanding that we can only see light that has had time to reach us. Since the universe is ever expanding, this creates a kind of cosmic boundary. Beyond this limit lies the unobservable universe, which could contain countless galaxies and phenomena that we currently have no access to, hidden from our mortal eyes. Scientists employ various tools and technologies to figure out the universe's bounds. Telescopes, both on Earth and in space, capture light from distant objects, allowing researchers to study their compositions and distances. By measuring the redshift of light, an effect where light stretches to longer wavelengths as the cosmos expands, astronomers can infer how far away these objects lie and map the universe's structure. The observable universe is estimated to be about 90 to 100 billion light-years in diameter. Within this vast expanse lies a kaleidoscope of galaxies, stars, and cosmic phenomena, each contributing to our understanding of the universe's origin, evolution, and eventual fate. Exploring this enormous framework can provide a glimpse not just into the makeup of our cosmos, but also into the very laws of nature that govern it. Telescopes are our windows into the universe, serving as powerful tools that enable us to observe distant galaxies, stars, and other celestial bodies. The versatility of modern telescopes plays a crucial role in expanding our understanding of the cosmos. Optical telescopes gather light from celestial objects, allowing us to view them in incredible detail, while radio telescopes detect the radio waves emitted from distant phenomena, revealing aspects of the universe that are invisible to the naked eye. One of the most significant advancements in astronomy has been the development of space telescopes like the Hubble Space Telescope. Positioned beyond Earth's atmosphere, these telescopes can capture clearer images without the distortion caused by air. Hubble has provided us with breathtaking photographs and invaluable data about galaxies billions of light-years away, giving us glimpses into the universe's early history and the formation processes of stars and planetary systems. Further extending our reach into the cosmos are technologies like spectroscopy. This technique analyzes the light emitted or absorbed by celestial objects, breaking it down into its constituent colors. By studying these spectra, scientists can determine the composition, temperature, density, and even movement of distant stars and galaxies. This understanding helps astronomers piece together the life cycles of these celestial bodies and how they impact the universe as a whole. In addition to telescopes and spectroscopy, advancements in computing and imaging techniques enhance our exploration capabilities. Computer algorithms process vast amounts of data collected, revealing hidden patterns and deep insights into the cosmos. With these tools, we continue to push the boundaries of our knowledge, inching closer to the edge of the observable universe and unveiling the mysteries that lie beyond. Each new discovery sparks curiosity, prompting us to look deeper into the vastness of space with wonder and excitement. The speed of light is a fundamental constant of nature and plays a crucial role in shaping the boundaries of our observable universe. Light travels at approximately 300,000 kilometers per second, and this remarkable speed determines how far we can see into the cosmos. Essentially, the universe is about 14 billion years old, which means that light has had about that long to travel to us from distant celestial bodies. This distance defines what we can observe, creating a vast yet limited view of space. When we look at stars or galaxies, we are not seeing them as they are right now, but rather as they were when the light first left them. For instance, if we observe a galaxy that is 7 billion light-years away, we are actually witnessing it as it appeared 7 billion years ago. This concept is known as the look-back time, and it highlights how our observations connect us to the history of the universe itself. Thus, the farther away an object is, the longer the light takes to reach us, allowing us to peer back into time. Moreover, the finite speed of light introduces an outer boundary, known as the cosmic horizon, beyond which we cannot receive information. This is not simply a limitation of our technology, it stems from the very nature of space and time itself. As the universe expands, the distance that light can travel becomes ever more constrained. Parts of the universe may be receding from us so quickly that their light will never reach our eyes, meaning that countless galaxies exist beyond our observational reach, forever shrouded in cosmic darkness. Understanding the implications of light speed reshapes our perception of the universe. It reveals a dynamic and ever-evolving cosmos where the observable limits are continually shifting. In this vast expanse, light serves both as a bridge to our past and a barrier to knowledge, inviting us to explore the mysteries hidden just beyond our cosmic horizon. Cosmic inflation is a theory that describes an extraordinary period of rapid expansion in the very early universe. This phase is believed to have occurred just a fraction of a second after the Big Bang, where the universe expanded exponentially, growing from subatomic scales to the size of a grapefruit in an unimaginably short time. This dramatic expansion helps to address several puzzling questions in cosmology, such as the uniformity of the cosmic microwave background radiation and why the universe appears so flat on a large scale. The relationship between cosmic inflation and the size of the observable universe is profound. Due to this inflationary period, regions of space that were once small became vastly separated. As a result, the observable universe we see today includes areas that were once in close proximity but became isolated due to the rapid expansion. This means that the universe's current size, which we estimate to be about 93 billion light-years in diameter, is a consequence of this initial rapid expansion. Inflation also sets the initial conditions for the formation of galaxies and large-scale structures we observe today. Tiny fluctuations in density caused by quantum mechanics during the inflationary period were stretched across the cosmos. Over time, these fluctuations evolved under the force of gravity, leading to the rich structures in the universe, including galaxies, clusters, and filaments we see today. Thus, cosmic inflation doesn't just explain the vastness of what we can observe. It also lays the groundwork for the universe's intricate design. This fascinating theory continues to be supported by a variety of observations, such as the detailed measurements of the cosmic microwave background and the distribution of galaxies. Each new piece of evidence deepens our understanding of how the universe came to be so large and uniform, igniting curiosity about both the early moments of existence and the mysteries that still lie beyond the farthest reaches of our sight. Redshifts are crucial to our understanding of the universe and its expansion. Simply put, when we observe distant galaxies, we notice that their light appears to be stretched towards the red end of the spectrum. This phenomenon occurs because these galaxies are moving away from us, and as they do, the wavelengths of their light increase. This shift towards red is akin to how the sound of a passing siren changes in pitch when the vehicle moves away, a concept known as the Doppler effect. The observation of redshifts in light from galaxies was first pioneered by astronomer Edwin Hubble in the early 20th century. By measuring the redshift of various galaxies, Hubble discovered that the more distant a galaxy is, the faster it seems to be moving away from us. This remarkable finding led to the revolutionary conclusion that the universe is expanding. Instead of being static, the cosmos is continuously stretching, suggesting that it has been in motion since the Big Bang. As astronomers continue to study redshifts, they have also uncovered more complex layers of information. The degree of redshift can not only indicate how fast a galaxy is receding, but it can also inform us about the universe's history and the rate of its expansion over time. This leads to the concept of the Hubble constant, a value that helps quantify how the expansion rate changes with distance. With ongoing advancements in technology and observational techniques, redshift measurements are allowing scientists to probe even deeper questions. They provide insights into the nature of dark energy, which is believed to be driving the accelerated expansion of the universe. Thus, redshifts are not just markers of movement. They are fundamental clues that help us decipher the grand and evolving story of our universe. The observable universe, while vast and stunningly intricate, is rife with mysteries that challenge even the best minds in science. One of the most profound enigmas is dark matter. Despite making up about 27% of the universe, dark matter remains invisible and undetectable by conventional means. It does not emit, absorb, or reflect light, which is why it escapes our direct observation. Scientists infer its existence through gravitational effects on visible matter, but what dark matter actually is remains one of the universe's greatest secrets. Various candidates exist, from weakly interacting massive particles to modifications of gravitational theory, but none have yet been conclusively observed. Similarly puzzling is dark energy, a force propelling the accelerated expansion of the universe. This mysterious energy composes approximately 73% of the cosmos and works against the pull of gravity. Discovered in the late 20th century, dark energy continues to baffle researchers. It is hypothesized to be a constant energy density in space, leading to the question of why this force exists at all and what role it plays in the future evolution of the universe. As we venture deeper into cosmology, understanding dark energy may also shed light on the ultimate fate of everything we know. Another significant mystery lies in the imbalance of matter and antimatter. According to the laws of physics, the Big Bang should have produced equal amounts of both. However, our universe is predominantly composed of matter. This discrepancy is deeply troubling for cosmologists and particle physicists alike. Several theories attempt to address this imbalance, suggesting possible interactions or decays that favored matter over antimatter during the universe's infancy. Resolving this issue could be key to understanding the fundamental nature of our universe. Finally, the question of cosmic inflation, the rapid expansion of the universe just after the Big Bang, poses its own set of challenges. While it explains the uniformity of the cosmos and its flatness, the precise mechanism behind inflation remains elusive. Multiple inflationary models exist, each proposing different pathways and driving forces. Investigating the origins of inflation could potentially unlock new insights into both the early universe and the fundamental laws governing all matter and energy. Each of these mysteries not only underscores the limits of current understanding, but also sparks curiosity and a relentless pursuit of knowledge as humanity gazes into the stars. The cosmic microwave background radiation, or CMB, is a pivotal piece of evidence in our understanding of the universe's origins and boundaries. This faint glow of light fills the universe and represents the afterglow of the Big Bang. When the universe was only about 370,000 years old, it cooled enough for protons and electrons to combine into hydrogen atoms, allowing light to travel freely. This relic radiation is still detectable today, marking the limits of our observable universe. The CMB serves as a snapshot of the universe at that early moment in time, revealing a uniformity across vast distances. By studying its temperature variations, known as anisotropies, scientists can glean insights into the universe's density, composition, and expansion rate. These fluctuations hint at the underlying structures that would eventually evolve into galaxies and clusters, providing clues about the universe's growth and the gravitational forces at play. Moreover, the CMB sets a tangible boundary on what we can observe. Due to the finite speed of light, we can only see light that has had time to reach us since the beginning of the universe. Thus, the radiation we detect today comes from the farthest observable reaches of space, about 13.8 billion years away. Beyond this limit lies a vast expanse that remains unseen and is fundamentally inaccessible, pushing the boundaries of our understanding. Ultimately, the study of the cosmic microwave background radiation not only enriches our knowledge of the universe's infancy, but also paints a picture of its fate. The data collected allows cosmologists to test various theories about the forces governing cosmic expansion and the eventual destiny of the universe itself. This astonishingly ancient light connects us to the very dawn of time, reminding us of the universe's vastness and the knowledge that still lies beyond our current reach. The Big Freeze, also known as heat death, is a fascinating theory that describes one potential fate of our universe. It hinges on the idea that the universe is continually expanding. As it expands, the energy within it spreads out over an ever-increasing volume of space. This leads to a gradual cooling of the universe over an unimaginably long time. Essentially, stars will exhaust their nuclear fuel, galaxies will drift apart, and all matter will eventually move to a state of near absolute zero. As time goes on, the universe will become increasingly sparse and dim. Stars will cease to shine, turning into white dwarfs, neutron stars, or even black holes. These remnants will slowly decay over trillions of years as they radiate energy away. Eventually, even black holes will evaporate, a process known as Hawking radiation, leaving behind a dark, cold void filled predominantly with elementary particles. In this ultimate scenario, the universe will approach a state where it is devoid of any usable energy. All physical processes will essentially come to a halt. This profound stillness is referred to as the heat death of the universe, where entropy, or the measure of disorder, reaches its maximum. During this period, there will be no places for life as we know it to exist, and the cosmos will be utterly silent. Thus, the Big Freeze presents a chilling yet scientifically grounded vision of the universe's end. Unlike more explosive theories, such as the Big Crunch, where the universe collapses back into a single point, the Big Freeze offers a haunting sense of solitude as the cosmos fades to a quiet, frozen eternity. The Big Crunch theory presents an intriguing perspective on the ultimate fate of the universe, one that contrasts sharply with the expanding universe scenario we observe today. This theory postulates that the universe, after a long period of expansion, could eventually reverse direction and begin contracting. As galaxies move closer together, the density of matter would increase, leading to dramatic changes in the cosmic landscape. This contraction would be fueled by the force of gravity, pulling everything, stars, galaxies, and even dark matter, back towards a central point. Imagine a giant cosmic balloon air being let out. As it deflates, the surface gets smaller, and everything that was once separated draws nearer. The culmination of this contraction could see the universe collapse into a singularity, a point of infinite density where the laws of physics as we know them break down. The concept of the Big Crunch raises many questions about the nature of space and time. If the universe were to experience this ultimate collapse, it could be followed by a new cycle of expansion, suggesting that our universe might go through infinite iterations of birth, life, and death. Such ideas stimulate considerable debate among scientists about the long-term behavior of cosmic structures and the fundamental nature of time itself. While current observations suggest that the universe is expanding at an accelerating rate due to dark energy, the Big Crunch remains a fascinating theoretical possibility. It reminds us of the dynamic and evolving nature of our cosmos, sparking our curiosity about what the future may hold in the grand tapestry of existence. The Big Rip is a fascinating scenario in cosmology that speculates on the ultimate fate of the universe. This theory suggests that the expansion of the universe, currently observed to be accelerating, may eventually lead to a catastrophic tearing apart of all matter. Under this hypothesis, the force driving the universe's acceleration, attributed to a mysterious entity known as dark energy, grows stronger over time. In the final moments, galaxies, stars, planets, and even atoms would be ripped apart, resulting in a universe that is nothing but a schematic of isolated energy streaks. Supporting evidence for the Big Rip comes primarily from the observation of distant supernovae. These celestial explosions appear dimmer than expected, indicating that the universe is expanding faster than it was in the past. Furthermore, studies of the cosmic microwave background radiation, an afterglow from the Big Bang, provide insights into the universe's structure and its rate of expansion. Certain models of dark energy suggest that if its density increases over time, we could be heading toward the Big Rip scenario. However, the Big Rip is just one among several potential outcomes of the universe's evolution. Competing theories, such as the Big Freeze and the Big Crunch, paint different pictures of the cosmos' fate. The Big Freeze posits that as the universe continues to expand, it will eventually cool to a point where all stars cease to shine, leading to a dark and lifeless expanse. This contrasts starkly with the Big Crunch, which suggests that gravitational forces could reverse the expansion, pulling everything back into a singularity. As for contradictions to the Big Rip, current observations of dark energy indicate that it may remain constant over time rather than intensifying. This would lead to a more gradual expansion rather than an explosive tearing apart of the fabric of space. Ultimately, while the Big Rip presents a dramatic thesis about the end of the universe, ongoing research in cosmology continues to refine our understanding of dark energy and its implications for the cosmos, keeping the door open to various possibilities for our universe's fate. The concept of a multiverse introduces a profound shift in our understanding of the cosmos. Traditionally, we envision our universe as a singular entity, complete with an edge or boundary that separates it from whatever lies beyond. However, the multiverse theory posits that what we recognize as our universe is just one of many, potentially infinite universes existing simultaneously. This notion challenges the idea that there is a definitive edge to our own universe. In a multiverse scenario, different universes may have distinct physical laws, constants, and even dimensions. Some might be nearly identical to our own, while others could be cosmologically very different. This variety implies that the concept of an edge might not apply uniformly across all these universes. Instead of one edge, there could be an endless landscape of universes, each with their own characteristics and properties, fundamentally reshaping our understanding of cosmic boundaries. This also raises intriguing questions about the origins and nature of our universe. If multiple universes exist, the events that shaped our universe might be just a small part of a much larger picture. For example, the inflation theory suggests that our universe underwent rapid expansion after the Big Bang, but in a multiverse context, this inflation could be occurring in countless other bubble universes as well. Each bubble might inflate differently, leading to a rich tapestry of diverse realities. Ultimately, the multiverse concept invites us to rethink our place within the cosmos. Rather than being at the forefront of a singular, bounded universe, we might be inhabiting a corner of an immensely more complex and grand structure of existence. This radical idea not only ignites curiosity and passion among cosmologists, but also propels humanity deeper into the mysteries of reality and the fundamental nature of existence itself. The question of whether the universe is finite or infinite sparks a captivating debate within cosmology. Advocates for an infinite universe argue that based on the principles of geometry, the cosmos could extend endlessly in all directions without an edge or boundary. This concept aligns with cosmological models suggesting that space is flat on a large scale. If the universe is indeed flat, it could stretch infinitely, allowing celestial bodies to exist forever, presenting an intriguing notion that the stars may flicker across an ever-expanding vastness. On the other hand, supporters of a finite universe point to the observable universe and its well-defined structure. They argue that when we examine the cosmic background radiation and the distribution of galaxies, we find clues indicating boundaries. Observations suggest that the universe has a finite age, approximately 13.8 billion years since the Big Bang. If we travel back through time, we may find a point of origin, implying the universe could be finite, encapsulated within an unseeable cosmic framework. Another compelling argument against the finite universe is the concept of cosmic inflation, which proposes that shortly after the Big Bang, the universe underwent a rapid expansion. This expansion could have brought distant regions into contact, giving the appearance of a larger, more complex structure than initially imagined. However, the finite model suggests that this expansion may eventually come to an end if gravitational forces prevail, potentially leading to a possible scenario where the universe collapses in on itself, resulting in a finite existence. In discussing these conflicting viewpoints, the debate highlights the limitations of our current understanding while emphasizing our quest for answers. Whether the universe is infinite or finite continues to inspire researchers to probe deeper into its mysteries. As we gather more observational evidence and refine our models, the truth behind this cosmic question may one day be revealed, but for now, it remains one of the most profound topics in modern science. String theory, a cutting-edge concept in theoretical physics, offers a fascinating perspective on the nature of the universe's boundaries. Unlike traditional particle physics, which describes particles as point-like objects, string theory proposes that fundamental particles are actually tiny, vibrating strands of energy, or strings. This idea extends our understanding of the universe beyond the conventional dimensions we experience, suggesting there could be more than the three spatial dimensions and one time dimension we are familiar with. In the context of the universe's boundaries, string theory introduces additional dimensions, potentially up to 10 or even 11. The dimensions beyond our everyday experience may be compacted and hidden at scales smaller than we can currently observe. This opens intriguing possibilities about the shape and structure of the universe itself. For example, some models suggest that the universe could be infinitely large with complex folded dimensions, eliminating the notion of a boundary in the traditional sense. According to this view, what we perceive as the universe's edges might merely be the limits of our current observational capacity. Moreover, string theory aligns with concepts of cosmology that explore the very origin of the universe. By integrating ideas from quantum physics and general relativity, string theory may help us understand how the universe began. The early moments after the Big Bang are particularly enigmatic, and string theory might provide a framework where quantum fluctuations could lead to the density waves that influence cosmic structures like galaxies. Consequently, it also raises questions about what lies beyond our observable universe and challenges our comprehension of space and time. While string theory does not offer definitive answers, it enriches the ongoing debate about the characteristics and extent of the universe. By proposing a multi-dimensional reality, it nudges scientists to reconsider what we understand about boundaries, not simply as physical limitations, but as part of a deeper, more complex cosmic tapestry. This exploration invites further inquiry into how potentially unobservable dimensions could shape the universe we engage with every day, ensuring that the quest for knowledge continues to expand our horizons. The concept of higher dimensions extends far beyond our everyday experience and plays a pivotal role in modern theories about the universe. Traditionally, we understand our world in 3 dimensions of space and 1 dimension of time. However, physicists explore the possibility that more dimensions exist, influencing both the universe's structure and its behavior. These additional dimensions could offer insights into unresolved questions about the cosmos and its ultimate boundaries. In theories such as string theory, higher dimensions are not merely a mathematical abstraction, but a fundamental aspect of reality. String theory posits that the smallest building blocks of the universe are not point-like particles, but rather tiny strings vibrating in multiple dimensions. According to this theory, our familiar 4 dimensions may be just a small part of a much larger cosmos, potentially involving as many as 10 or 11 dimensions. These additional dimensions might be compacted or curled up, making them imperceptible at everyday scales, but significant at quantum or cosmological levels. The allure of higher dimensions lies in their potential to unify the fundamental forces of nature. By integrating gravity, electromagnetism, and the nuclear forces into a single framework, higher dimensions can offer a comprehensive understanding of the universe's workings. This unification suggests a seamless fabric connecting all particles and forces, challenging our perception of space and time. It invites us to reconsider the very nature of reality and sparks our curiosity about what lies beyond our immediate experience. Moreover, the quest to understand higher dimensions stretches our imagination about the universe's limits. If these dimensions exist, they may redefine the boundaries of our understanding, suggesting that the universe is far more complex and interconnected than we realize. This ongoing exploration encourages scientists to probe deeper into the nature of existence, revealing the infinite possibilities that could shape the cosmos we inhabit. As researchers continue to investigate this intriguing territory, we come closer to uncovering the mysteries that lie beyond our perceptual grasp. The observable universe is a vast expanse that stretches over 13 billion light-years in every direction, containing everything we can currently detect or measure. However, beyond this horizon, the mystery only deepens. Current scientific models suggest that the universe continues beyond what we can see, though we have no direct evidence of this beyond our observational limits. Theories suggest that the universe may be infinite, extending far beyond the observable realm filled with countless galaxies, clusters, and possibly even different physical laws and constants. This means that although we can visualize a bubble of space around us, there is an entire cosmos beyond it, potentially teeming with planets and stars that remain forever out of our reach. Another intriguing possibility is that the universe is not just infinite, but also forms part of a multiverse. This concept proposes that our universe is one among many, each with its own distinct properties. Some might be governed by different physical laws, leading to a diverse range of structures or phenomena, all coexisting in a larger network of universes. Moreover, regions of space that lie beyond the observable universe could be expanding faster than the speed of light due to cosmic inflation. This rapid expansion means that many areas will never be accessible to us, forever outside our grasp. The quest to understand what lies beyond the observable universe not only pushes the boundaries of science, but also ignites our imagination about the cosmos that surrounds us, encouraging deeper exploration into the very fabric of reality. The cosmic horizon represents the limit of what we can see in the universe. Beyond this boundary lies a realm that is shrouded in mystery, yet scientists, driven by curiosity and the laws of physics, have developed various hypotheses about what might exist beyond it. This boundary is determined by the age of the universe and the speed of light, meaning we can only observe objects whose light has had enough time to reach us since the Big Bang. One of the primary tools scientists use in these hypotheses is the concept of cosmic inflation. This theory suggests that in the moments just after the Big Bang, the universe underwent exponential expansion, vastly increasing its size. If inflation occurred, then beyond our observable universe, there could be regions of space that are vastly different from our own, each potentially containing countless galaxies and structures that look nothing like what we see within our cosmic horizon. Additionally, scientists explore the idea that the universe could be infinite. If this is true, then there might be an endless expanse of space teeming with galaxies, stars, and possibly even life, far beyond what we can currently detect. This concept challenges the very nature of the universe's structure, suggesting that our observable patch is merely a tiny fragment of a far grander reality. Finally, some hypotheses even venture into the speculative realms of multiverse theory. This intriguing idea proposes that our universe might be just one among many, each with its own unique physical laws and constants. Such a notion stretches our understanding of reality and invites us to ponder the fundamental nature of existence itself. While these ideas remain theoretical, they showcase human ingenuity in seeking to unravel the cosmos's ultimate secrets, igniting wonder about the vast unknown that extends beyond our current sight. As we gaze into the cosmos, we are acutely aware of the limitations imposed by the observable universe. The universe extends beyond the reach of our telescopes, yet scientists wield a range of tools and methods that offer glimpses into these inaccessible regions. One of the most promising approaches involves the study of cosmic background radiation. This faint afterglow, a remnant from the Big Bang, fills the universe and holds clues about its early stages, hinting at what lies beyond our observational capabilities. Another powerful tool is the use of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects. By detecting these waves, we can infer events that occurred in regions far beyond our direct view, such as black hole mergers or neutron-star collisions. Observatories dedicated to gravitational wave detection have revolutionized our understanding of these cataclysmic phenomena, paving the way for insights into the universe's structure and history. Additionally, simulations and theoretical models play a crucial role in this exploration. Scientists create sophisticated computer models that replicate the universe's evolution, applying the laws of physics to predict behaviors in regions we cannot observe directly. These models help us understand the influence of dark matter and dark energy, mysterious components that dominate the universe yet remain poorly understood. Lastly, advancements in technologies like radio and infrared astronomy allow scientists to peer through cosmic dust and gas, revealing objects simply hidden from standard optical observations. By employing various wavelengths, researchers can gather critical information about galaxies, stars, and planetary systems that exist beyond our observational reach. Through these innovative methods, we are not just limited to what we can see, but can extend our understanding of the vast cosmos significantly. Gravitational waves, ripples in the fabric of spacetime, have transformed our understanding of the universe, especially in how we study its most violent and distant phenomena. When massive astronomical events occur, such as the collision of neutron stars or black holes, they create disturbances in spacetime that we can detect here on Earth. Instruments like the Laser Interferometer, Gravitational Wave Observatory, or LIGO pick up these faint signals, providing us with crucial information about the events that generated them. By analyzing the patterns of these gravitational waves, scientists can infer the properties of the objects involved in their creation. For example, the frequency and amplitude of the waves can reveal the masses of the merging objects and the distance from which the waves originated. This is possible because the waves carry information about the dynamics of the event itself. The more massive the objects, the more intense the gravitational waves they produce. Such analysis allows astronomers to backtrack, reconstructing the processes that occurred during these spectacular cosmic events. Moreover, gravitational waves do not interact with matter in the same way light does, allowing them to pass through the universe largely unimpeded. This means that they can reveal information about regions of space that may be obscured by dust or gas, making them a powerful tool for exploring the cosmos. They offer a new lens through which we can observe astronomical phenomena, providing insights that complement traditional electromagnetic observations like those from telescopes. The importance of gravitational waves extends beyond individual events. They forge a new way of understanding the fundamental nature of the universe. As more events are detected and analyzed, astronomers stand on the brink of uncovering new phenomena, revealing the mysteries of dark matter, dark energy, and the complex evolution of the cosmos itself. With each wave detected, we edge closer to a more profound grasp of our universe's structure and history. To understand the size and scale of the universe beyond what we can see researchers utilize several fascinating methods that combine observational data with theoretical models. The portion of the universe we can observe is known as the observable universe, which extends for approximately 13.8 billion light-years from Earth. However, the entire universe is believed to be much larger and could potentially be infinite. One significant aspect of this measurement relies on the expansion of the universe. Edwin Hubble's discovery in the early 20th century that galaxies are moving away from us has profound implications. By measuring how quickly these galaxies recede, scientists can infer their distances and calculate the rate of expansion known as the Hubble constant. This expansion leads to the conclusion that the universe is growing beyond our ability to observe it fully, giving clues about its overall scale. Moreover, researchers turn to the cosmic microwave background radiation, which is the afterglow of the Big Bang. This radiation is nearly uniform across the sky and provides essential information about the early universe, its composition, and its geometry. By analyzing fluctuations in this background radiation, scientists can estimate the total mass and density of the universe, which helps in understanding its shape and extent. Astrophysicists also model the universe's evolution using simulations based on the laws of physics. These models take into account the effects of dark energy and dark matter, mysterious components that make up most of the universe's mass-energy content. By incorporating these factors and running simulations, researchers can generate projections of the universe's overall size and provide estimates that often suggest a universe far larger than the observable portion, possibly stretching infinitely in all directions. Through these approaches, the quest to comprehend the cosmos continues, revealing awe-inspiring insights about the vastness beyond what our eyes can perceive. Dark matter and dark energy represent two of the most enigmatic pieces of the cosmic puzzle, fundamentally reshaping our understanding of the universe beyond what we can directly observe. While only about 4% of the universe is made up of ordinary matter, the remaining universe is dominated by dark matter and dark energy. This vast expanse of hidden components influences the structure and expansion of the universe, guiding scientists as they seek to comprehend the cosmos in its entirety. Dark matter, which makes up roughly 26% of the universe, is crucial for understanding gravitational forces at work on a cosmic scale. It does not emit, absorb, or reflect light, making it invisible to traditional methods of observation. However, its presence is inferred through its gravitational effects on visible matter. For instance, galaxies rotate at such speeds that they should, based solely on visible mass, tear themselves apart. Dark matter provides the gravitational glue that holds these galaxies together, revealing that what we can see is just the tip of the cosmic iceberg. On the other hand, dark energy constitutes approximately 70% of the universe and is responsible for the observed acceleration in the universe's expansion. This mysterious force works against gravity on the grandest scales, pushing galaxies further apart. As scientists probe deeper into the cosmos, the interplay between dark energy and dark matter offers clues about the fate of the universe, hinting at scenarios where galaxies might drift endlessly apart or collapse into a cosmic web of structures with dark energy as the dominant force driving their evolution. Investigating these hidden components allows astronomers to ponder questions beyond our observable capabilities. The dynamics of dark matter and dark energy not only reshape the universe's structure, but also invite speculation about its ultimate fate. As research continues, the quest to understand the roles of dark matter and dark energy remains a vital component in unlocking the secrets of a universe that stretches far beyond the horizons we can currently observe. Quantum mechanics and cosmology may seem like two separate realms of science, but they intersect in fascinating ways when probing the mysteries of the universe's edge. At its core, quantum mechanics deals with the behavior of the smallest particles in our universe, such as electrons and photons, while cosmology addresses the grand-scale structures and dynamics of the universe itself. The intersection occurs where the fundamental laws of physics governing these tiny particles influence the fabric of the cosmos. One of the most intriguing areas of this intersection is the study of cosmic events during the universe's infancy, soon after the Big Bang. Quantum fluctuations, minute variations in the energy of empty space, played a crucial role in shaping the distribution of matter across the universe. These fluctuations, rooted in the quantum realm, expanded during cosmic inflation, which caused the universe to grow exponentially in a fraction of a second. As a result, the seeds for galaxies, stars, and cosmic structures we observe today were sown at that time. Additionally, concepts like black holes intertwine quantum mechanics and cosmology. Black holes, with their immense gravitational forces, pose challenges for our understanding of both gravity and quantum physics. Theoretical explorations suggest that at the edge of a black hole, where gravity becomes unbearably strong, quantum effects dictate the behavior of particles and information. Some speculate that a complete theory of quantum gravity, which would unite these two fields, could unveil the secrets of black holes and perhaps even the nature of the universe's edge. Finally, the quest to understand dark energy and dark matter, which together comprise around 95% of our universe, also lies in the realm where quantum mechanics and cosmology meet. The quantum properties of these enigmatic components could provide insight into the expansion of the universe. As we continue to explore and merge these diverse fields, we stand on the brink of discoveries that could reshape our understanding of the universe and its enigmatic boundaries. Throughout history, cultures around the world have envisioned the edge of the universe in remarkably diverse and imaginative ways. In ancient Mesopotamia, the universe was often depicted as a vast, flat expanse covered by a domed sky. This celestial dome was believed to hold the heavens and gods above, while the earth lay beneath. The edge of existence, in their minds, was characterized by a mysterious boundary where the physical world met the divine, hinting at an otherworldly dimension. In contrast, the ancient Greeks contributed significantly to cosmological thought, proposing the concept of a spherical universe. Philosophers like Ptolemy and Aristotle imagined the cosmos as a series of concentric spheres, with the Earth at the center. For them, the universe had a definite edge, where the fixed stars resided in a celestial sphere that bounded human experience. This idea evolved into more complex theories during the Renaissance, leading to a more heliocentric view, where the edge became less about physical boundaries and more about understanding the cosmos as something vast and expansive. Eastern philosophies also offered unique perspectives. In Hindu cosmology, the universe is seen as cyclical rather than linear, constantly undergoing cycles of creation and destruction. The idea of an edge is less about a physical limit and more about the flow of time and existence. Similarly, in Chinese cosmology, concepts such as yin and yang illustrate the interconnectedness of all things, suggesting that the universe doesn't possess a definitive boundary, but instead flows into a state of balance. Modern scientific views have shifted towards a more nuanced understanding of the cosmos, yet the cultural and philosophical images of the universe's edge continue to resonate. The boundaries of our universe are understood in terms of observable limits tied closely to the expansion of space itself. Despite these advancements, the rich tapestry of human imagination illustrates that the quest to understand what lies beyond the known universe is a profound journey that transcends science, inviting us to ponder our place in a much larger infinity. The nature of the universe, whether it is boundless or finite, raises profound questions about our existence and the place we occupy within the cosmos. If the universe is infinite, it suggests a reality without limits, where the possibilities for life, events, and even the laws of physics may stretch endlessly. In this scenario, some might find a sense of comfort through the concept of infinite opportunities and limitless exploration. Everything we've known or can conceive might exist somewhere out there, reinforcing the idea that our individual lives hold significance in a larger, possibly infinite tapestry. Conversely, if the universe is finite, it presents a different set of implications. A finite universe implies that there are boundaries to our existence, both in physical space and potentially in time. This can evoke a sense of urgency to understand our surroundings and our role within it. It raises the question of whether the universe itself had a beginning and whether it might someday have an end, leading to philosophical considerations about mortality and legacy. The finite nature of the cosmos might compel us to seek meaning in the brief flicker of our existence against a backdrop of cosmic enormity. Both views urge us to think about the implications of our mortality and the nature of consciousness. In an infinite universe, does the realization of countless other possible versions of reality diminish the significance of human experience? Or does it elevate our understanding of interconnectedness? Alternatively, in a finite cosmos, does the awareness of limitations encourage us to cherish each moment more deeply, to find purpose in our fleeting lives? Ultimately, the questions posed by the universe's nature serve as a mirror reflecting our hopes, fears, and aspirations. Whether boundless or finite, the cosmos invites contemplation not just about the stars above us, but also about the essence of our being, our search for knowledge, connection, and meaning in what may well be one of the finest mysteries of existence. The concept of the universe's edge, or boundaries, has profound implications not only for cosmology, but also for our understanding of human existence. Current theories suggest that the universe is constantly expanding, and this expansion leads to questions about what lies beyond its observable limits. This expanded view of the cosmos invites us to ponder not just the physical nature of the universe, but also our place within it. Philosophically, the idea of an edge pushes us to reconsider our notions of existence and significance. If the universe has boundaries that we cannot see or understand, what does that mean for humanity's role in the vast expanse of creation? Are we simply insignificant specks in a boundless territory, or is there an intrinsic value to our existence as conscious beings capable of pondering these very questions? The mystery of the universe's edge can evoke feelings of awe, prompting reflections on purpose and connection. Furthermore, theories about the universe's edge encourage a vision of cosmology that is ever evolving. As scientists discover new elements of our cosmos, the philosophical implications ripple through cultures and belief systems. The more we learn, the more we question if there are definitive answers to existence or if it is a never-ending journey of inquiry. This dynamic also opens doors to dialogue between science and philosophy, challenging rigid boundaries and inviting more holistic perspectives on life and existence. Ultimately, the questions surrounding the universe's edge serve as a mirror, reflecting not only our quest for knowledge, but our innate desire to understand who we are within this grand tapestry of existence. The search for answers becomes intertwined with our search for meaning, weaving a narrative that speaks to our shared curiosity and the deep connections we all share as explorers of the universe. The search for the edge of the universe and the age-old philosophical quests for meaning reveal intriguing parallels that reflect humanity's fundamental longing for understanding. Both endeavors invite us to confront questions that may never have definitive answers. As astronomers stretch their instruments and gaze into the depths of space, they are not just chasing physical boundaries, they are also probing existential edges, just as philosophy brings forth deeper mysteries. The more we learn about the universe's structure, the more questions emerge about its origin, its fate, and our place within it. Another parallel connects the methods employed in both disciplines. Philosophical inquiry relies on critical thinking, reasoning, and dialogue, whereas scientific exploration uses observation, experimentation, and sometimes abstract theory. Both paths thrive on curiosity and the desire to connect with something greater than ourselves. Whether contemplating the idea of a multiverse in quantum physics or questioning the nature of good and evil in ethics, both scientists and philosophers share a relentless pursuit for clarity amidst ambiguity. Finally, the notion of perspective plays a crucial role in both quests. Just as a philosophical view can shift our understanding of morality or existence, so too can our cosmic perspective alter our sense of belonging in the vastness of space. When we ponder the unimaginable scales of the universe, we can find ourselves feeling both insignificant and at the same time integral to its story. Consequently, this exploration of the universe and the philosophical pursuit of meaning both serve to enrich our comprehension of ourselves, our origins, and our ultimate purpose in the grand tapestry of existence. When we contemplate the concept of the universe's edge, we embark on a journey that challenges our traditional understanding of time and space. The universe is often described as being boundless, expanding outward, and evolving. However, imagining an edge raises critical questions about what lies beyond it and how that might inform our perception of the cosmos. At the heart of this inquiry is the nature of space itself. In a finite universe, one might envision a boundary akin to the surface of a balloon. As the balloon expands, all points on its surface move away from each other, yet there remains no actual edge in three-dimensional space. This analogy helps illustrate how space might be structured. Rather than a hard boundary, the universe could be curved, making it possible to travel in a straight line and eventually return to your starting point. Such concepts encourage us to see space as a dynamic continuum rather than a static backdrop. Time, in parallel, becomes an intriguing companion to this discussion. If the universe has an edge or boundary, then time itself might also have a beginning or an end. Current theories, including the Big Bang, suggest that time itself originated with the universe, implying that there was before that is difficult for us to comprehend. This interplay suggests that our conventional linear view of time may need to be re-evaluated, leading to theories that account for alternate timelines or cyclical natures of existence. Ultimately, grappling with the idea of the universe's edge encourages us to embrace the limitations of our understanding. It pushes us to explore the very fabric of reality, where time and space may not function in the ways we instinctively believe. Whether pondering a cosmic limit or limitless expanse, each inquiry deepens our appreciation of the universe's intricate nature and our place within it, inviting us to look beyond the visible into the realms of the unknown. Theories regarding the end of the universe can profoundly shape our ethical perspectives about how we live today. When we ponder the final fate of everything, the heat death of the universe, the Big Crunch, or even a potential rebirth through cosmic inflation, we inevitably confront our insignificance in the vast cosmos. This realization can instill a sense of urgency, prompting individuals to value their experiences more deeply and prioritize meaningful connections with others. Many people respond to the concept of an eventual cosmic ending by embracing a more hedonistic or experiential approach to life. The idea that time is limited can encourage a focus on pleasure, personal relationships, and fulfilling experiences. It leads to the notion that if existence is fleeting, we ought to maximize every moment, celebrating love, adventure, and joy. Such a mindset echoes philosophies that emphasize living in the here and now, resonating with traditions that highlight the importance of mindfulness and presence. Conversely, the awareness of an ultimate end can also inspire a sense of responsibility towards future generations. If we understand that our time is but a blink in the cosmic timeline, it can galvanize efforts to further our collective well-being. Many ethical philosophies, including utilitarianism and deep ecological perspectives, advocate for stewardship of the Earth in light of our interconnectedness. By considering the universe's fate, we may feel compelled to ensure that our actions today do not devastate the environment or hinder the potential for future life. Ultimately, how we interpret the universe's end can lead to a delicate balance between seizing the moment and considering the long-term consequences of our actions. These ethical frameworks encourage us to reflect on the legacy we wish to leave, not just for ourselves, but for those who will come after us in this vast and mysterious cosmos. So, as we ponder the universe's fate, we not only speculate on what lies ahead, but also actively shape the narrative of our current existence. In recent years, we have witnessed remarkable technological advancements that significantly enhance our ability to explore the universe. One of the most groundbreaking developments is the rise of space-based telescopes. The James Webb Space Telescope, launched in late 2021, represents a leap forward in our observational capabilities. Its advanced infrared technology allows scientists to peer further into the cosmos than ever before, offering insights into the formation of stars and galaxies and even the atmospheres of exoplanets. In addition to telescopes, artificial intelligence is becoming a powerful ally in astronomical research. By utilizing machine learning algorithms, scientists can sift through vast amounts of data collected from space missions. This technology identifies patterns and anomalies that human researchers might miss, accelerating discoveries. For instance, AI has played a crucial role in identifying new exoplanets by analyzing light curves and recognizing the subtle signs of planets transiting their stars. Moreover, advancements in propulsion technology are opening new frontiers for space exploration. Concepts such as solar sails and ion propulsion offer more efficient means of traveling farther into space. Solar sails harness the pressure emitted by sunlight to propel spacecraft, while ion propulsion systems use electric fields to accelerate ions, offering a steady thrust over extended periods. These technologies could significantly shorten travel time for future missions to distant destinations, such as Mars and beyond. Finally, the development of miniaturized satellites, or CubeSats, is revolutionizing how we explore the universe. These small but powerful satellites can be launched in swarms, allowing researchers to gather data from multiple points in space simultaneously. Their low cost and versatility make them ideal for monitoring cosmic phenomena and conducting experiments in diverse environments, from our atmosphere to the far reaches of the solar system, all while pushing the boundaries of our understanding of the universe itself. Recent space missions have significantly enhanced our understanding of how the universe began and its farthest reaches. One of the most groundbreaking endeavors has been the James Webb Space Telescope, launched in late 2021. Unlike its predecessor, the Hubble Space Telescope, which primarily observed in optical and ultraviolet wavelengths, Webb is designed to see in infrared. This allows it to look further back in time, peering through cosmic dust and observing ancient galaxies as they were just a few 100 million years after the Big Bang. These observations reveal essential information about the formation of the first stars and galaxies. By studying the light emitted from these distant objects, astronomers can infer the conditions of the early universe. The data from Webb tells us more about the elements present, the speed of galaxy formation, and how these early structures influence the cosmic landscape. Such insights push the boundaries of our knowledge regarding cosmic evolution and the universal laws that govern it. Another significant mission is the European Space Agency's Gaia spacecraft, which has been mapping our Milky Way galaxy with astonishing precision. Gaia has created a three-dimensional map of stars, measuring their distances and movements. This stellar census is crucial because it helps scientists understand the structure of the Milky Way and its interaction with surrounding galaxies, contributing to our broader understanding of galaxy formation and evolution in the universe. Together, these missions provide a clearer picture of the universe's edge, where it transitions from the familiar night sky into incomprehensible vastness. They offer new insights into cosmic phenomena, such as dark matter and dark energy, which are believed to drive the expansion of the universe. With ongoing and future missions planned, our perspective on the cosmos continues to expand, unraveling mysteries that have captivated humanity for centuries. Computer simulations play a crucial role in helping scientists explore and understand the vastness of the universe, particularly the regions beyond our observable limits. The observable universe is just a small fraction of the entire cosmos, defined by the distance light has traveled since the Big Bang. To grasp what lies beyond this horizon, scientists turn to advanced simulations that model cosmic phenomena based on our current understanding of physics. These simulations utilize numerical models that incorporate the fundamental laws of physics, such as gravity and radiation. By simulating the behavior of galaxies, dark matter, and cosmic background radiation, researchers can create vast cosmic landscapes that reveal how structures might evolve over billions of years. For example, scientists can recreate the early universe's conditions, providing insights into how matter interacted right after the Big Bang, which helps inform theories about cosmic inflation and the distribution of galaxies. Moreover, simulations can effectively visualize complex processes that are impossible to observe directly. For instance, through simulations, researchers can study the interplay of various forces and interactions at a scale far beyond what we can currently observe with telescopes. They can analyze the formation and behavior of galaxy clusters and explore dark energy, which drives the universe's accelerated expansion. These visual representations help scientists form hypotheses that can be tested with observational data. Ultimately, while computer simulations cannot replace observational astronomy, they enhance our understanding by offering a virtual window into regions of the universe we may never directly observe. As technology continues to advance, these simulations become increasingly sophisticated, enabling scientists to refine their models of the cosmos and deepen our understanding of the universe's past, present, and future. As we stand on the brink of a new age in space exploration, several potential breakthroughs in technology promise to redefine our understanding of the cosmic frontier. One of the most exciting developments is the advancement of artificial intelligence. Powerful algorithms can process immense amounts of data from telescopes and space missions much faster than any human could. This ability allows us to identify celestial bodies, hidden patterns, and even signals that might indicate the presence of extraterrestrial life. These AI systems can scan vast regions of space and provide insights that were previously unimaginable, pushing the boundaries of what we know about the universe. Moreover, the advent of new propulsion technologies, such as ion drives and solar sails, could revolutionize space travel. Unlike traditional chemical rockets, these advanced propulsion systems can provide continuous thrust over long periods, enabling spacecraft to reach distant destinations more efficiently. Imagine a journey to the outer planets or beyond, taking weeks rather than years. These technologies could open up the solar system for exploration, allowing us to send probes to the moons of Jupiter or the distant reaches of the Kuiper Belt. They may even one day help us reach other star systems. Another promising area is the development of space telescopes that surpass the capabilities of the Hubble Space Telescope. New designs, such as the James Webb Space Telescope, aim to observe the universe in unprecedented detail, particularly in the infrared spectrum. With this forward-looking technology, we can peer into the atmospheres of exoplanets, search for the building blocks of life, and gain insights into the formation of galaxies. Such observations could lead to significant discoveries about the nature of when and how life may arise beyond Earth, fundamentally shaping our understanding of our place in the cosmos. Finally, advancements in materials science are paving the way for designing more durable and efficient spacecraft. Innovations such as lightweight composites and self-repairing materials could make future space missions safer and more sustainable. With these technologies at our disposal, we can dream of long-term human habitats on Mars or even the construction of space stations in deeper space. Each of these developments contributes to a growing arsenal of tools that can expand our exploration and understanding of the universe, pushing us closer to answering humanity's most profound questions about existence and our connection to the cosmos. International collaborations play a crucial role in exploring the universe's limits by pooling together diverse resources, knowledge, and expertise from institutions around the globe. The vastness of space and the complexity of its phenomena often require specialized skills and technologies that no single country can encompass alone. By collaborating, nations can tackle larger challenges and share the costs of expensive projects, making ambitious scientific endeavors more feasible. One of the most compelling examples of such collaboration is the International Space Station, where astronauts from different countries live and work together. This unique laboratory enables groundbreaking research in astrophysics, biology, and materials science, all under the backdrop of microgravity. The cooperative effort of space agencies like NASA, ESA, JAXA, and Roscosmos highlights how shared goals can lead to advancements in knowledge and technology that benefit humanity as a whole. Furthermore, large-scale observatories and experiments, such as the Large Hadron Collider or the upcoming James Webb Space Telescope, involve contributions from scientists around the world. The exchange of ideas and data fosters innovation that enhances our understanding of cosmic phenomena. International collaborations not only expedite the discovery process, but also create a global network of researchers who can collectively analyze complex data and troubleshoot unexpected challenges. By working together, countries can enhance diplomatic ties and inspire the next generation of scientists and explorers. As we push the boundaries of our understanding of the universe, these collaborative efforts remind us that the exploration of space is a shared human endeavor, transcending borders and uniting us in our quest for knowledge about the cosmos. Scientists have developed sophisticated techniques to utilize data from satellites to map the farthest reaches of space, significantly expanding our understanding of the universe. Satellites act as powerful tools equipped with advanced instruments that collect a variety of information from distant celestial objects. Through both direct imaging and remote sensing, these satellites gather data on phenomena such as light radiation and cosmic microwave background, which help reveal the structure and composition of the universe at unimaginable distances. One of the primary ways satellites assist in mapping space is through the measurement of light emitted from galaxies. Instruments on board these satellites can analyze light spectra, determining the chemical composition, age, and motion of galaxies billions of light-years away. This capability allows scientists to construct a three-dimensional map of the universe, highlighting the distribution of galaxies and galactic clusters in relation to one another. Such insights are crucial for understanding the universe's expansion and the underlying forces that govern it. Not only do satellites capture light, but they also detect cosmic radiation. For instance, the cosmic microwave background radiation is a remnant from the Big Bang, providing a snapshot of the universe when it was just a few 100,000 years old. Satellites like the Planck Observatory have been instrumental in measuring this faint afterglow, offering critical data about the universe's early conditions, growth of cosmic structure, and the overall geometry of space. Moreover, satellites contribute to mapping distant cosmic events such as supernova or gravitational waves, which can influence how we perceive the universe. By observing these phenomena from a distance, scientists can gather evidence about the life cycles of stars and the behavior of black holes. Together, these discoveries from satellite data help piece together the cosmic puzzle, enriching our knowledge about the vast, mysterious expanse that surrounds us. Artificial intelligence is revolutionizing our understanding of the universe, especially when it comes to processing and interpreting vast amounts of data from its edge. The cosmos is an immensely complex and dynamic place, and our observational tools like telescopes and satellites collect massive quantities of information about distant galaxies, cosmic radiation, and other celestial phenomena. The sheer volume of data can be overwhelming, but AI steps in as a powerful ally, expertly sifting through this information to identify patterns and anomalies that human researchers might overlook. One of the primary roles of AI in cosmology is its ability to enhance data analysis. Machine learning algorithms can be trained to recognize specific features in datasets, such as the light signatures of different stars or the subtle gravitational waves caused by colliding black holes. By using AI to analyze this data, astronomers can accelerate discovery processes, producing results in a fraction of the time it would take through traditional analysis. This efficiency gives scientists the opportunity to explore deeper realms of our universe, pushing the boundaries of our knowledge further than ever before. Moreover, AI helps in the interpretation of complex astrophysical models. Simulating cosmic events like supernova explosions or galaxy formations requires intricate calculations and approximations. AI can assist in refining these models by ingesting extensive datasets and learning from them, leading to more accurate predictions. This iterative process improves our understanding of how galaxies form and evolve, the nature of dark matter, and the expansion of the universe itself, which are critical questions in modern cosmology. As we venture further into the edges of the universe, the collaboration between AI and human researchers holds great promise. It enables us to untangle the mysteries of cosmic phenomena and interpret them in ways that were previously thought to be unattainable. By harnessing the power of artificial intelligence, we are not just observing the universe. We are deepening our understanding of its fundamental processes, expanding our horizons, and inspiring a new generation of scientists to continue the quest for knowledge beyond the stars. Black holes are some of the most fascinating phenomena in the universe, and their existence provides significant insights into the boundaries of our cosmos. At their core, black holes are regions in space where gravity pulls so strongly that nothing, not even light, can escape from them. This powerful gravitational force arises from a large amount of mass concentrated in a small area, typically formed from the remnants of massive stars after they undergo supernova explosions. Understanding black holes allows scientists to grapple with the concept of boundaries in the universe. These boundaries can be thought of in terms of the event horizon, which is the point of no return surrounding a black hole. Once an object crosses this threshold, it is irretrievably drawn into the black hole. This notion challenges our perception of space and time, as the event horizon delineates a limit beyond which the known laws of physics begin to break down. It raises profound questions about the very nature of reality itself, inviting speculation on the fabric of the universe. Moreover, black holes serve as laboratories for testing our understanding of fundamental physics, especially the theories of relativity and quantum mechanics. They push the boundaries of our knowledge, forcing scientists to re-evaluate how gravity interacts with space-time. As researchers delve deeper into the study of black holes, they uncover new dimensions of the universe, including potential links to the mysterious concepts of dark matter and dark energy. In this way, black holes can be viewed as gateways to the unknown, igniting human curiosity about what lies beyond the observable universe. They challenge us to ponder the ultimate fate of matter and energy, suggesting that the universe is not just a vast expanse of galaxies, but a complex, interconnected tapestry where the edges of our understanding are constantly being tested and redefined. Supermassive black holes, those colossal entities found at the centers of galaxies, exert a profound influence on cosmic structure and our understanding of the universe's fate. Ranging from millions to billions of times the mass of our Sun, these black holes are not just passive objects. They actively shape their surroundings. Their gravitational pull affects the movement of stars and gas within their host galaxies, effectively acting as a cosmic anchor. As they consume surrounding material, they can emit incredibly powerful jets of radiation, illuminating vast regions of space and influencing star formation. These black holes also play a vital role in the evolution of galaxies. It is widely believed that the growth of supermassive black holes is intertwined with the formation and development of galaxies themselves. As matter spirals into these dense centers, it creates disks of material that can heat up and emit energetic radiation. This process can regulate star formation, sometimes suppressing it by expelling gas from the galactic core through powerful winds, ultimately affecting the galaxy's structure and dynamics. When it comes to mapping the universe, supermassive black holes serve as vital markers. Their immense gravitational fields distort the fabric of space-time around them, especially in areas where net gravity from multiple black holes comes into play. These distortions can help astronomers trace the distribution of dark matter, an unseen component that constitutes most of the universe's mass. By studying the movements of stars and gas influenced by these black holes, scientists can glean insights into the large-scale structure of the cosmos. Furthermore, the presence of supermassive black holes may give clues about the ultimate fate of the universe. Observations suggest that the growth and activity of these black holes are linked to cosmic events such as mergers between galaxies. Such interactions not only help in understanding how galaxies evolve, but also in pondering scenarios involving cosmic expansion and eventual contraction. As researchers continue to map our universe, supermassive black holes stand out as beacons of information, guiding our quest to decipher the vast mystery of cosmic destiny. The black hole information paradox is a fascinating and thought-provoking concept that challenges our understanding of the universe. It arises from the conflict between quantum mechanics and general relativity, two pillars of modern physics. At its core, the paradox questions what happens to information, that is, the data that describes particles and their states when they fall into a black hole. According to classical physics, once something crosses the event horizon, it cannot escape, leading to the seemingly absurd conclusion that information is lost to the universe forever. This dilemma becomes particularly significant when we consider the nature of black holes. If black holes can destroy information, that would violate a fundamental principle of quantum mechanics, which insists that information must always be conserved. So, theories about the information paradox not only grapple with the fate of information, but also suggest limitations to our current understanding of the physical laws that govern the universe. They raise important questions about the ultimate nature of reality, potential boundaries of physics, and what might be beyond our current frameworks. Various proposed solutions to the paradox have emerged, indicating that black holes may actually leak information back into the universe in some form, possibly through what is called Hawking radiation. This idea suggests an intricate connection between quantum mechanics and gravitational forces. It implies that black holes could be more than just regions where gravity reigns supreme, but may also be gateways or conduits of information that deepen our understanding of the cosmos. Such theories push us to rethink our ideas about the fabric of reality itself and the limits of scientific knowledge. Ultimately, the discussion about black hole information paradoxes serves to highlight the still unanswered questions about the universe. As scientists continue to explore these intricate puzzles, they open the door to new theories that could redefine the boundaries of cosmic understanding. This ongoing search gives us a glimpse into the profound complexity of the universe, a reminder that in the world of physics, edges are often just gateways to wider horizons. Wormholes are fascinating theoretical constructs in the field of cosmology and physics. Often described as shortcuts through spacetime, they are solutions to the equations of general relativity proposed by Albert Einstein. Imagine two distinct points in the universe connected by a tunnel-like structure. This enables not only travel between widely spaced locales in our own universe, but also raises intriguing questions about what lies beyond. The concept of wormholes acting as passages to regions outside of our universe is both tantalizing and complex. Some theories suggest that these wormholes could connect our universe to other parallel universes or different dimensions entirely. This idea stems from the notion of a multiverse, where countless universes exist simultaneously, each with its own set of physical laws and constants. If wormholes can connect disparate regions of space-time, they may also serve as bridges to these alternate realities. However, wormholes remain purely theoretical at this point, and no empirical evidence has been found to confirm their existence. Moreover, even if they do exist, maintaining stability in such structures poses significant challenges. The idea of exotic matter, which possesses negative energy density, is often mentioned as a necessary ingredient to keep a wormhole open. Without it, any attempt to traverse such a passage could result in collapse, making it impossible for anything, including light, to escape. As we continue to explore the vast and mysterious universe, the allure of wormholes persists in inspiring both scientists and science fiction enthusiasts alike. They open up possibilities for time travel, interdimensional travel, and much more, stimulating the imagination and encouraging us to question the very fabric of reality. Whether we will ever navigate through such cosmic doorways remains an open question, but the journey of discovery certainly adds to the wonder of our universe. Black holes have long captured the imagination of scientists and the public alike, not just for their mysterious nature, but for the tantalizing implications they carry regarding the fabric of the cosmos. One of the theories suggesting that black holes could be gateways to other universes comes from the concept of a wormhole. Wormholes are hypothetical passages through space-time that could connect distant points in our universe, or even link to entirely separate universes altogether. Essentially, the idea is that when matter is swallowed by a black hole, it could emerge from a white hole in another universe, providing a bridge through which travel might be possible. The mathematics supporting this idea is rooted in the theory of general relativity, which describes how gravitational fields can curve space-time. Some scientists propose that the singularity of a black hole, the point at which density becomes infinite, might lead to a different dimension of space-time. In this scenario, the material that enters the black hole does not need to vanish forever. Instead, it may follow a peculiar journey through an alternate realm, becoming part of another reality shaped differently from our own. Moreover, this possibility feeds into the multiverse theory, which posits that our universe is just one of potentially an infinite number of universes. Each of these universes could have different laws of physics, creating rich variations on how reality could manifest. If black holes truly serve as bridges to these other realities, they would not only be gateways to understanding our universe, but also the innumerable others that lie beyond our perception. While these ideas remain theoretical and largely speculative, they inspire a fascinating dialogue within the scientific community. The challenge of conclusively proving or disproving these theories lies in the realm of advanced physics, where intuition often runs counter to observed realities. As research in astrophysics and quantum mechanics progresses, the prospect of black holes as conduits to parallel universes continues to ignite curiosity and wonder, reminding us of the vast unknowns that still inhabit the cosmos. Hawking radiation, a concept proposed by the brilliant physicist Stephen Hawking, plays a fascinating role in understanding the universe, particularly through the enigmatic nature of black holes. At its core, Hawking radiation suggests that black holes are not entirely black, but instead emit particles due to quantum effects near their event horizons. This process occurs because of the complex interactions between particles and the gravitational pull of the black hole, leading to what some might describe as black holes slowly leaking energy into space. The implications of Hawking radiation extend far beyond the mysterious boundaries of black holes. By demonstrating that black holes can emit radiation and, over an incredibly long time, lose mass, it opens up unique avenues for probing how these cosmic giants interact with their surroundings and the universe. This phenomenon suggests that black holes are temporary structures within the cosmic landscape rather than eternal prisons of matter and energy, challenging our traditional views of them as ultimate endpoints in the universe. As we study these extraordinary emissions, we gain insights not only into black holes, but also the fundamental laws of physics. Hawking radiation brings together elements of general relativity and quantum mechanics, spurring discussions about how they reconcile with one another. This intersection is crucial in the quest to understand the universe's edge as we approach the boundaries of known physics. Understanding how these processes work can lead to insights about the limits of space and time itself. Moreover, the potential detection of Hawking radiation could revolutionize our comprehension of the cosmos. If scientists were able to observe the radiation from black holes, it might provide crucial clues about the history of the universe, the nature of dark matter, and the future fate of cosmic structures. Thus, Hawking's profound insight not only reshapes our understanding of black holes, but also invites us to re-examine the very fabric of the universe we inhabit, opening a portal to the mysteries that lie beyond. Dark matter, despite being invisible and undetectable through conventional means, plays a crucial role in shaping the universe. It comprises about 27% of the total mass-energy content of the cosmos. This mysterious substance does not emit, absorb, or reflect light, making it incredibly elusive. However, its existence is inferred from the gravitational effects it exerts on visible matter, such as stars and galaxies. One of the most significant influences of dark matter is its role in galaxy formation. Early in the universe's history, small fluctuations in density led to the clumping of matter. Dark matter formed the foundational scaffolding around which visible matter could accumulate. Galaxies formed in these dense regions, ultimately resulting in the complex structure we observe today. Without dark matter's gravitational pull, galaxies would struggle to hold their stars and gas together, resulting in a very different and perhaps much less structured cosmos. Dark matter also significantly impacts the large-scale structure of the universe. It dictates the arrangement of galaxy clusters and superclusters, forming a vast web-like network. Observations of this cosmic web show that galaxies are not distributed evenly. Instead, they cluster along the filaments of dark matter, creating a complex tapestry that outlines the gravitational web of dark matter itself. This alignment reveals patterns that enhance our understanding of both the distribution of galaxies and the overall expansion of the universe. Furthermore, understanding dark matter helps scientists explain phenomena such as gravitational lensing. When light from distant galaxies passes near massive clusters of matter, it gets bent due to gravity. This bending reveals the presence of unseen mass, primarily from dark matter. Such observations not only validate the existence of dark matter, but also provide insights into the universe's expansion rate and its ultimate fate. As we delve deeper into this topic, we uncover the intricate and often astonishing ways dark matter influences the cosmos around us. Dark energy is one of the most intriguing and enigmatic components of our universe. It makes up about 70% of the total energy density of the cosmos and is believed to be the driving force behind the current accelerated expansion of the universe. The concept gained traction in the late 90s when observations of distant supernovae indicated that the universe was not just expanding, but that the rate of expansion was actually increasing. This unexpected finding challenged traditional cosmological models and led scientists to consider dark energy as a crucial factor in understanding our universe. There are several theories attempting to explain the nature of dark energy. One prominent idea is that dark energy is a constant energy density that fills space homogeneously, often referred to as the cosmological constant. This concept originated with Albert Einstein when he introduced the cosmological constant into his equations of general relativity, initially to allow for a static universe. However, it fell out of favor until the discovery of the universe's accelerated expansion rekindled interest in this idea, suggesting that something is energetically pushing galaxies apart. Another theory is called quintessence, which postulates that dark energy is dynamic and changes over time and space. Unlike the cosmological constant, which remains constant, quintessence could vary in strength, influencing how the universe expands differently across time. This theory leaves room for changes in the cosmos, potentially allowing for complex interactions between dark energy, matter, and gravity. Yet another perspective presents a more radical departure from conventional thinking. Some researchers suggest that our understanding of gravity itself may need revision, proposing that modifications to Einstein's theory could explain cosmic acceleration without invoking dark energy at all. These theories reflect the cutting-edge research within cosmology, where the ultimate nature of dark energy remains a profound mystery. As scientists continue to gather data and refine their models, we inch closer to unveiling the secrets of dark energy and its pivotal role in shaping the universe we observe today. Detecting and measuring dark matter presents a unique challenge for scientists, primarily because this mysterious substance does not emit, absorb, or reflect light, making it invisible to conventional observation methods. Instead, researchers have developed indirect techniques to infer its presence by observing its gravitational effects on visible matter. For instance, when we study galaxies, we notice that they rotate at surprisingly high speeds. According to the laws of gravity, the visible matter, the stars and gas, should not be spinning as quickly as they do unless there is a significant amount of unseen mass exerting additional gravitational force. This unseen mass is thought to be dark matter. One of the most compelling pieces of evidence for dark matter comes from galaxy clusters. When scientists analyze the motion of galaxies within these clusters, the speeds at which they move suggest there is much more mass present than what we can observe. By measuring the gravitational lensing effect, where light from distant objects is bent around massive foreground objects like galaxy clusters, researchers can map out the distribution of this unseen mass. This bending of light acts like a cosmic magnifying glass, revealing the presence and amount of dark matter through its influence on the light's path. Moreover, experiments in underground laboratories are designed to directly detect dark matter particles. These facilities use sensitive detectors buried deep underground to shield themselves from cosmic rays and other background radiation. The idea is that if dark matter particles interact with ordinary matter, albeit very rarely, they might produce detectable signals. Scientists utilize different techniques, such as looking for tiny recoil movements in heavy nuclei within these detectors, providing further insights into the properties of dark matter. In addition to these approaches, advanced simulations play a critical role in understanding dark matter's role in the evolution of the universe. By modeling gravitational interactions, scientists can predict how dark matter should influence galaxy formation and distribution over cosmic time. Through a combination of gravitational observation, detection attempts, and modeling, researchers are piecing together the puzzle of dark matter, driving us closer to understanding this elusive component of our universe. Dark energy is one of the most intriguing mysteries in modern cosmology. This mysterious force accounts for approximately 70% of the universe and plays a pivotal role in its expansion. Initially, scientists believed that the expansion of the universe would slow down due to gravitational forces. However, the discovery of dark energy revealed that instead, the universe is accelerating in its expansion. This unexpected behavior reshapes our understanding of cosmic destiny. As dark energy continues to dominate the energy composition of the universe, it will directly influence its long-term fate. Current theories suggest that if dark energy remains constant and unchanged, the universe will continue to expand at an accelerating rate. This scenario could lead to a future where galaxies drift farther apart from one another, ultimately resulting in a cold and sparsely populated expanse, a state sometimes referred to as the Big Freeze. In this chilling vision, stars will either burn out or drift away, leaving behind a dark and silent cosmos. Alternatively, if dark energy evolves in some way, various fates for the universe could emerge. Some hypotheses suggest that dark energy might increase over time, leading to a catastrophic scenario known as the Big Rip. In this scenario, the force of dark energy becomes so overwhelming that it tears apart galaxies, stars, planets, and even the very fabric of space-time itself, resulting in a dramatic end to the universe as we know it. At this point, we have only scratched the surface of understanding dark energy and its consequences for the universe. Ongoing research, involving advanced telescopes and surveys, is crucial to unraveling the secrets held by this enigmatic substance. By studying distant supernovae and galaxy clusters, scientists hope to further comprehend how dark energy shapes the cosmos and determines the ultimate fate of everything within it. Theories about dark matter have significantly shifted our understanding of the universe, particularly when it comes to its structure and the concept of its edge. Traditional models of the universe suggested that it is primarily composed of visible matter, which includes stars, planets, and galaxies that we can see with our telescopes. However, dark matter, an invisible and mysterious substance, is thought to make up about 27% of the total mass energy content of the universe. This challenges the existing models by implying that there is much more to our universe than meets the eye. Dark matter does not emit, absorb, or reflect light, making it extremely difficult to detect directly. Instead, most of our understanding comes from its gravitational effects. Observations show that galaxies spin at such high speeds that they should tear apart if only the visible matter were present. Dark matter provides the necessary gravitational glue that holds these galaxies together, thus suggesting we need to rethink not just what composes our universe, but also its edges and limits. These realizations lead to intriguing questions. What happens at the edges of the universe if dark matter is present? Conventional models frame the universe as a vast expanse with a well-defined edge, but dark matter suggests a more complex and perhaps infinite structure. Models incorporating dark matter propose that the universe might not have a sharp boundary, but may instead exhibit a continuous fabric of gravitational influences that stretches beyond our visual horizon. As scientists delve deeper into the characteristics of dark matter, they afford fascinating insights into the structure of our universe, particularly concerning the presence of unseen forces that shape galaxies. When astronomers measure the speed at which stars and gas orbit around the center of galaxies, they expect to see these speeds decrease with distance from the core, much like how planets move in our solar system. However, observations over several decades have shown a surprising consistency in velocities, maintaining higher speeds even far from the galaxy's center. This unexpected phenomenon indicates that a significant amount of mass must be present beyond the visible matter that we can observe, like stars and gas. Scientists have theorized that this could be evidence for dark matter, an invisible substance that does not emit or interact with electromagnetic radiation, making it undetectable by standard observational methods. Dark matter is believed to make up about 25% of the universe's total mass energy content. The implications of this discovery are profound. Dark matter acts as a gravitational glue, holding galaxies and galaxy clusters together, thus influencing their formation and evolution over time. Researchers have found that the way rotation curves flatten out at greater distances suggests that this unseen mass is distributed in a halo around galaxies. This idea revolutionizes our understanding of cosmic structure and points to a universe dominated not by the matter we can see, but by forces that remain elusive. Understanding galactic rotation curves not only highlights the existence of dark matter, but also raises further questions about the fundamental nature of reality. What is dark matter made of? Are there other forces at play beyond our current understanding? Each discovery opens new avenues for inquiry, keeping astronomers and physicists engaged in exploring the enigmatic fabric of our universe. Dark matter and dark energy are two of the most intriguing and enigmatic components of our universe. Though they are fundamentally different in nature, their interplay at the edges of the cosmos could significantly shape our understanding of the universe's structure and fate. At its core, dark matter is a form of matter that does not emit, absorb, or reflect light, which makes it invisible and detectable only through its gravitational effects. It forms the scaffolding upon which galaxies and galaxy clusters are built, exerting a gravitational pull that keeps galaxies inside clusters bound together. Dark energy, on the other hand, is a mysterious force driving the accelerated expansion of the universe. While dark matter works to clump and hold matter together, dark energy works to push everything apart. As we probe the edges of the universe, scientists are investigating how these two components interact. One intriguing possibility is that dark matter could influence the distribution of dark energy. For example, if dark matter density fluctuates, it might create regions where dark energy is more or less effective. This could lead to complex behaviors in the expansion of the universe, perhaps producing areas where the rate of expansion varies more than expected. Moreover, understanding this interaction could reveal insights about the fabric of space-time itself. If dark matter and dark energy are connected in ways we do not yet fully grasp, they might hold the key to answering some of the universe's most profound questions: the nature of gravity, the fate of cosmic structures, and the ultimate destiny of our universe. As observational technology advances and we delve deeper into the cosmos, we continue to uncover the mysteries that dark matter and dark energy present at the very edges of existence. Cosmic horizons represent the boundaries of our observable universe. These horizons are not physical barriers, rather, they are a consequence of the finite speed of light and the age of the universe. As we look into the depths of space, we are also looking back in time. Light from distant galaxies takes billions of years to reach us, and this journey means there are regions of the universe whose light has not yet had the opportunity to reach Earth. The primary cosmic horizon, known as the observable universe, encompasses everything that can currently be seen. This region extends about 13.8 billion light-years from Earth. This distance reflects the age of the universe and the time light has had to travel since the Big Bang. Beyond this threshold lies a vast expanse of space that remains unobservable because the light has not had enough time to arrive at us. Consequently, our understanding of the universe's full extent is inherently limited, leading to the remarkable realization that there might be infinitely more cosmos beyond our reach. In addition to the observable universe, we encounter the concept of the event horizon, particularly in the context of black holes. This is another type of cosmic boundary where not even light can escape due to the extreme gravitational pull. These event horizons mark the point of no return for objects falling into a black hole. However, the broader cosmic horizons shape our understanding because they highlight the limitations of observation, fostering a sense of mystery about what lies beyond the universe we can see. Understanding cosmic horizons invites a deeper appreciation of the universe's structure and our place within it. It emphasizes the significant role of light and time in shaping our observations, reinforcing that much of the cosmos forever remains hidden from our view, an intriguing reminder of the vastness and complexity of the universe that continues to fuel cosmic exploration and scientific inquiry. The concept of a cosmic horizon and that of an infinite universe are two fascinating ideas in cosmology that explore the boundaries of our understanding of the universe. The cosmic horizon is essentially the limit of what we can observe from our vantage point on Earth. It is the boundary beyond which light has not had enough time to reach us since the beginning of the universe. This horizon defines a sphere around us, marking the edge of the observable universe, and is influenced by the expansion of space itself. On the other hand, an infinite universe suggests that the cosmos extends endlessly in every direction, beyond any boundaries we might define. If the universe is truly infinite, it means there is no edge or limit to what exists. This infinite expanse would contain an infinite number of galaxies, stars, and possibly even planets, suggesting a vastness that can be both awe-inspiring and difficult to comprehend. The idea of an infinite universe challenges our perception of space and time, raising questions about the nature of existence itself. These two concepts intersect intriguingly. While our observable universe is limited by the cosmic horizon, we cannot definitively conclude that the universe itself is finite. In fact, many cosmologists propose that the universe could be infinite, even if only a finite portion of it is accessible to us through observation. This creates a tension between what we can know through observation and what might exist beyond that boundary. Ultimately, the cosmic horizon serves as a practical limitation on our ability to explore the universe, while the notion of an infinite universe prompts us to ponder what lies beyond our observational capacities. Together, these ideas invite us to marvel at the universe's complexity, encapsulating the wonders of cosmology and reminding us that the quest for understanding is still ongoing. The accelerated expansion of the universe raises profound questions about its structure and boundaries. First identified through observations of distant supernovae, this expansion means that galaxies are moving away from each other at an increasing rate. This behavior suggests that the cosmos is not becoming static. It is stretching and evolving in ways that challenge our traditional views of the universe's limits. As acceleration takes hold, the idea of a boundary becomes murky. If galaxies are receding faster, some of them may eventually move beyond our observable reach. Over cosmic time, this could lead to a situation where we are unable to see parts of the universe that once were visible, making us feel increasingly isolated in our own cosmic neighborhood. In this sense, the universe has no definitive edge. Rather, it is continuously expanding, making its true scale difficult to ascertain. Moreover, the cause of this acceleration is attributed to a mysterious force known as dark energy. Accounting for about 70% of the universe, dark energy defies our conventional understanding of gravitational forces. This enigmatic driver raises further questions. Is dark energy constant, or does it change over time? How does it influence the overall shape and fate of the universe? These are critical points that scientists are still exploring as they navigate a universe that is both vast and ever-expanding. The implications of accelerated expansion extend beyond mere boundaries. They invite us to rethink fundamental concepts about the universe's past and future. With each discovery, astronomers and cosmologists gather more clues about how our universe operates. The rapid pace at which it expands presents not just obstacles, but opportunities for deeper understanding as we probe the age-old mysteries of existence and our celestial home. The expansion of the universe is one of the most significant discoveries in modern cosmology, fundamentally altering our understanding of the cosmos. The first clues about this expansion emerged in the early 20th century when astronomer Edwin Hubble observed that distant galaxies were moving away from us. This phenomenon is known as redshift. As light from these galaxies travels through space, it stretches, raising its wavelength and shifting it toward the red end of the spectrum. Hubble's observations demonstrated not only that the universe was expanding, but that the further away a galaxy is, the faster it appears to be moving away. Over the years, researchers have accumulated a wealth of evidence that supports this expansion model. One key piece is the cosmic microwave background radiation, which is the afterglow of the Big Bang. Detected in the mid-20th century, this faint radiation fills the universe and serves as a snapshot of the infant cosmos when it was just about 300,000 years old. Detailed measurements of this background radiation, particularly from satellites like the Wilkinson Microwave Anisotropy Probe, have provided a wealth of information about the universe's early conditions, eventually leading to insights about its expansion. In addition, the discovery of dark energy has further refined our understanding of the universe's expansion dynamics. This mysterious force, which appears to be driving an accelerated expansion, was first inferred in the late 1990s through observations of supernovae. Astronomers discovered that these stellar explosions were fainter than expected, indicating that they were much farther away than presumed. These findings suggested that not only is the universe expanding, but the rate of expansion is actually increasing over time, a surprising and perplexing conclusion. Together, these pieces of evidence present a clear and coherent picture of the dynamism of the universe's expansion. From Hubble's initial observations to the intricate data from cosmic background radiation and the role of dark energy, scientists continue to deepen their understanding of how our universe evolves. The expanding universe is not merely a static phenomenon, it is a vibrant, continually unfolding saga of cosmic evolution that challenges our perceptions and shapes our understanding of what lies beyond the stars. Crossing a cosmic horizon is a fascinating thought experiment in cosmology. The cosmic horizon represents the limit of the observable universe, the boundary beyond which light from distant objects has not yet had time to reach us. If, somehow, we were able to cross this horizon, the observable universe would expand dramatically. We would begin to see galaxies, quasars, and cosmic phenomena that had previously been hidden from our view due to the finite speed of light and the age of the universe. As we cross this boundary, an intriguing experience awaits. We would be privy to a much younger universe, observing light that has taken billions of years to reach us. Picture witnessing the formation of new stars and galaxies, events that occurred long before the light we currently see from our own local neighborhood began its journey. This would give us a unique glimpse into the universe's past, allowing us to analyze the conditions that led to cosmic structures as we know them today. Moreover, crossing the cosmic horizon could alter our understanding of space and time. The universe is expanding, and some galaxies are moving away from us faster than light due to this expansion. By transcending our current limits, we might explore areas where the expansion rate allows us to see objects not directly observable from our position. Such a phenomenon would challenge our notions about the size and extent of the universe and raise profound questions about what lies beyond our current understanding. Finally, it's essential to consider the implications of meeting potential new forms of matter, or even dark energy in these fields beyond the cosmic horizon. This knowledge could unlock mysteries surrounding the forces that govern our universe. Although we remain grounded in our current perspective, the idea of crossing this barrier encourages scientific curiosity about the cosmos and inspires deeper questions about existence on a grand scale. The expansion rate of the universe is a fundamental aspect of cosmology, influencing not only its present condition, but also its ultimate fate. Since the Big Bang, the universe has been stretching, with galaxies receding from each other. This expansion is measured by a value known as the Hubble constant, which tells us how quickly galaxies are moving away based on their distance from us. The current rate of expansion is not just an observation, it carries deep implications for what might happen to our universe in the distant future. At the heart of this discussion is the role of dark energy, a mysterious force that appears to be driving the acceleration of the universe's expansion. From observations, it became clear that the expansion was not just continuing, but actually speeding up. This suggests that dark energy constitutes a significant portion of the universe's total energy content. As the universe expands under the influence of dark energy, galaxies will become increasingly separated, leading to a scenario referred to as the Big Freeze. In this increasingly cold, empty universe, stars will flicker out and galaxies will drift apart into isolation. Conversely, if the expansion rate were to slow down or reverse due to some gravitational force, we might see a different fate altogether. The universe could end in a big crunch, where all matter collapses back into a highly dense state. Scholars speculate about scenarios where various forms of unseen matter could change the dynamics of expansion and lead us towards different outcomes. However, current evidence strongly suggests that we are in an era of accelerating expansion, making such a scenario less likely. The expansion rate of the universe intricately intertwines with its destiny. With the current acceleration driven by dark energy, the universe is on a path toward a vast, cold future where galaxies drift apart indefinitely. This ongoing expansion not only shapes our understanding of cosmic evolution, but also poses profound questions about the ultimate fate of all matter and energy in existence. The concept of the space-time continuum is fundamental to our understanding of the universe and its boundaries. Space and time, once thought to be separate entities, are woven together into a four-dimensional fabric that governs the behavior of everything in the cosmos. This intertwining suggests that events are not just located in space, but are also situated within a complex framework of time, prompting profound questions about the limits of our universe. One significant implication of this concept is the nature of the universe's expansion. The Big Bang theory, which describes the universe's birth from a hot and dense state around 14 billion years ago, suggests that space itself has been stretching since that very moment. As the universe expands, it raises questions about what lies beyond the observable boundaries. The edge of the universe, if it even exists, is not a solid wall, but rather a fluid concept that moves and shifts as space continues to expand. Furthermore, the idea of a finite yet unbounded universe illustrates a captivating paradox. Imagine the surface of a balloon. As it inflates, every point on its surface moves away from every other point, yet the surface itself has no edges or boundaries. This analogy can be applied to our understanding of the universe. Although it may be expanding, it might not have a true boundary in the traditional sense. Instead, the universe could curve back on itself, creating a closed structure that has no definitive end. In examining theories about the universe's boundaries, the space-time continuum challenges our desire to pinpoint a specific edge. It allows for intriguing possibilities, including alternate dimensions or multiverse concepts, broadening the scope of what could lie beyond our observable universe. This leads to exciting discussions within cosmology about the nature of reality and our place within it, keeping us engaged in the endless mysteries of the cosmos. Albert Einstein's theories of relativity, particularly his general theory, have profoundly shaped our understanding of the universe's structure. Unveiled in the early 20th century, these theories shifted the paradigm from Newtonian physics, emphasizing not just gravity as a force, but rather as a curvature of space-time itself. This idea proposes that massive objects, like stars and planets, warp the fabric of space and time around them, leading to the phenomenon we perceive as gravity. This new perspective has significant implications for cosmology, the study of the universe's origin, evolution, and ultimate fate. For instance, the curvature of space-time helps explain the behavior of galaxies and the motion of celestial bodies. Instead of viewing gravity as a simple pull between masses, we now understand it comprehensively as an interaction that influences the flow of time and the shape of the universe itself. Einstein's equations allow scientists to model various cosmic scenarios such as black holes, neutron stars, and the dynamics of an expanding universe. One of the most striking predictions of Einstein's general relativity is the concept of an expanding universe. Observations made in the 20th century confirming that galaxies are moving away from us align perfectly with the predictions of this theory. This realization has led to the conclusion that the universe began with a singular event known as the Big Bang, lending insight into its age, approximately 13.8 billion years, and its ongoing expansion. Furthermore, Einstein's insights have directed modern astrophysics in seeking to understand dark matter and dark energy, mysterious components that make up a significant portion of the universe. As these elusive entities interact with the fabric of space-time, they challenge and refine our understanding of the cosmos, jump-starting ongoing research and theoretical explorations that continue to this day. In reflecting on Einstein's contributions, we grasp a more intricate narrative of the universe, one intricately woven by the interplay of gravity, time, and the very structure of space itself. Time plays a crucial role in our understanding of the universe and its limits. To grasp the nature of the universe, we first need to recognize that time and space are deeply intertwined. They form a four-dimensional fabric known as spacetime, a concept introduced by Albert Einstein. Within this framework, events are not just tied to their spatial coordinates, they also hinge on when they occur. This connection shapes how we perceive the universe and its boundaries. The age of the universe, estimated to be about 13.8 billion years, gives us a perspective on the limits of what we can observe. Light travels at a finite speed, so when we look deep into space, we are effectively looking back in time. The observable universe is defined by the limit of the light that has had time to reach us since the Big Bang. This means that while the universe itself may extend far beyond what we can currently observe, our grasp of its total size is constrained by the time that has passed. Moreover, as the universe continues to expand, the distance that light can travel increases, pushing those limits even further away. This expansion affects our understanding of cosmic events and structures beyond our observational reach. While we can see the cosmic microwave background radiation, which is a relic from the very early universe, there are regions beyond this visible horizon that we will never be able to experience directly. Time thus acts as both a guide and a boundary in our quest for cosmic knowledge. The role of time in defining the universe's limits is fundamental. It shapes our observations, influences our theories, and defines the very boundaries of what we can know about the cosmos. As scientists continue to explore the relationships between time, space, and the expanding universe, they uncover deeper insights that not only expand our comprehension of the cosmos, but also ignite our sense of wonder about what lies beyond the visible horizon. The fabric of space-time is an intricate tapestry that weaves together the vast cosmos, dictating how celestial bodies interact and how light travels. When we talk about alterations in this fabric, we're delving into phenomena like gravitational waves, black holes, and the expansion of the universe. Each of these events not only offers clues to their individual behaviors, but also hints at underlying mysteries concerning the universe's boundaries. As objects with immense mass, such as black holes, distort space-time around them, They create ripples in the fabric of the universe. These ripples can be detected by sophisticated instruments here on Earth, revealing the dynamics of events that occurred billions of light years away. Understanding these vibrations helps scientists interpret not just the gravitational interactions, but also offers insights into what exists at the farthest reaches of the universe. Could they suggest structures or even realities beyond our visible universe? Alterations can also occur during events like supernovae, where massive stars explode and leave behind immense voids that warp space-time. These dramatic occurrences can push the boundaries of our understanding of how matter and energy work together, potentially leading us to hidden aspects of the cosmic edge. As we study these variables, we inch closer to deciphering what lies beyond our observable universe. Moreover, considering the cosmic expansion, alterations in space-time can indicate whether the universe is flat, open, or closed. Each scenario paints a different picture of the universe's fate, whether it will continue expanding indefinitely, eventually collapse, or reach a balance. These factors not only reveal the universe's architecture, but also invite deeper questions. What lies at the edge of our universe? Could it be a gateway to regions we cannot yet comprehend? Through these explorations, we not only unveil parts of the universe's hidden narrative, but also expand our understanding of existence itself. The concept of a space-time without edges challenges our traditional perceptions of the universe and our place within it. In classic understandings, we often envision a universe that is bounded, that has a beginning or an end. Think of a perfectly contained realm like a box. But if we consider a universe that extends infinitely in both space and time, the implications can be profound not only for science, but also for philosophy. Without edges, the notion of boundaries disappears. This raises questions about the nature of reality itself. Is our universe truly infinite, or is it part of a more complex structure, perhaps even a multiverse with realms beyond our observation? An unbounded space-time suggests continuity, where every point in the universe transitions seamlessly into another. Philosophically, this ignites discussions about the meaning of existence and whether there are ultimate truths or resolutions to be found within an endless cosmos. Moreover, the absence of edges leads to inquiries about causality and time. If time extends infinitely backward and forward, does this imply that every event is somehow predetermined or interconnected, shaping a tapestry of existence rather than isolated moments? Such considerations provoke deeper reflections about free will, destiny, and our ability to affect the cosmos on both personal and universal scales. Additionally, this idea prompts a re-evaluation of human significance. In a universe without boundaries, individual lives may seem small, yet they become part of an intricate and vast system that is constantly in motion. This interconnectedness can offer a sense of meaning, suggesting that every action, no matter how minute, contributes to the unfolding story of the universe, emphasizing our role as conscious participants in a boundless reality. Recent discoveries in quantum gravity have opened up new avenues of understanding regarding the universe's boundaries, a topic that has fascinated scientists and enthusiasts alike for generations. At the heart of this exploration is the need to reconcile two fundamental pillars of modern physics: general relativity, which explains gravity on a grand scale, and quantum mechanics, which describes the behavior of particles at the smallest scales. The quest to bridge these theories has revealed profound insights into the very nature of space, time, and the universe itself. One of the remarkable developments in this field is the concept of spacetime as a dynamic entity rather than a static stage for cosmic events. Research has suggested that at the quantum level, spacetime may not be smooth or continuous. Instead, it appears to possess a granular structure, reminiscent of a fabric woven from discrete units. This idea challenges traditional views of the universe's boundaries, suggesting that they might not be as fixed as once thought. Instead, these boundaries could emerge from underlying quantum processes, fundamentally altering our perception of cosmic limits. Moreover, recent advances in string theory and loop quantum gravity have introduced the notion that the very fabric of the universe might be interlinked through a web of quantum states. These theories imply that what we consider the universe's edge may actually be a complex interplay of quantum information and gravitational interactions. This understanding raises intriguing questions about the nature of black holes, which are often thought of as boundaries where traditional physics breaks down. Instead of viewing these as absolute limits, scientists are now investigating how quantum gravity may allow information to escape from these regions, leading to a more nuanced understanding of what lies beyond. As research continues, we find ourselves on the cusp of a paradigm shift. The boundaries of the universe are no longer mere figments of our imagination, but rather realms of active inquiry where quantum mechanics and gravitational forces dance in a complex rhythm. Each new discovery not only deepens our knowledge, but also leaves us wondering about the fundamental structure of reality itself, urging us to contemplate the infinite possibilities that lie beyond our current understanding. With each advancement, we draw closer to a more complete picture of the cosmos and our place within it. The discovery of extraterrestrial life has the potential to profoundly alter our understanding of the universe, particularly regarding its edge, both literally and metaphorically. Historically, the edge of the universe has been considered in terms of its physical boundaries, defined by the vastness of space and the observable universe. Yet, if we were to find life beyond our own planet, it could lead to a re-evaluation of not only where the universe ends in space, but also how we perceive our place within it. One of the most significant implications of discovering extraterrestrial life would be the idea that life is not an isolated phenomenon restricted to Earth. This realization could suggest that the universe is teeming with life, possibly existing in environments previously thought to be inhospitable. This perspective raises questions about how galaxies and cosmic structures might influence the distribution of life across the universe, inviting us to rethink concepts of cosmic isolation or uniqueness. Moreover, the presence of extraterrestrial civilizations could indicate that we are part of a dynamic cosmos where life evolves under varying conditions. This new understanding may lead scientists to investigate how life forms interact with their environments and how these relationships shape both planetary systems and galactic neighborhoods. Such insights could redefine our views on cosmic evolution, migration, and the interconnectedness of celestial phenomena. Ultimately, the discovery of extraterrestrial life might shift our focus from pondering what lies beyond the physical edge of the universe to contemplating the profound implications for existence itself. Rather than defining our universe's edge strictly in terms of cosmic limits, we could begin to view it as a vibrant frontier, rich with discovery and an endless tapestry of life that challenges our notions of solitude in the cosmos. Communicating with potential civilizations beyond our observable universe presents a range of daunting challenges that stem from the very nature of the universe itself. First and foremost is the vastness of space. The observable universe stretches for about 13.8 billion years in every direction. While we can see light from distant stars and galaxies, the portions of the universe beyond our observational limits remain entirely unknown. This immense distance creates significant barriers. Even if we were to send a signal, it may never reach another intelligent species. If they exist, they could be separated from us by unimaginable distances or even darkness, making meaningful contact a formidable challenge. Another major hurdle is time. The universe is not static, it is constantly expanding. This expansion means that galaxies move away from each other, sometimes at speeds that exceed the speed of light due to the fabric of spacetime stretching. By the time a message reaches another civilization, they may have evolved, vanished, or moved beyond reach. Furthermore, the time it takes for our signal to travel may be on such a scale that it could span generations, perhaps even millennia, before we receive a response or the other civilization comprehends our attempt at communication. Technological limitations also play a crucial role. Our current methods of sending messages, like radio waves, have limitations. These signals diminish over distance and can be disrupted by cosmic phenomena such as gas clouds or gravitational waves. It raises the question, what if other civilizations have developed different technologies, or perhaps they use forms of communication we have yet to even conceive? Without understanding their methods, our attempts at reaching out could easily go unnoticed or misunderstood. Finally, there's the philosophical aspect. Since we can only base our understanding of life on our own experience, we may struggle to comprehend how another intelligent species thinks, perceives the universe, or even what it understands as communication. The variation in languages, symbols, and cultural contexts could create profound misunderstandings. Therefore, while the possibility of contacting extraterrestrial civilizations fuels our imagination, the multitude of barriers, physical, technological, and conceptual, makes it a complex endeavor steeped in uncertainty. The discovery of exoplanets, or planets outside our solar system, has significantly expanded our understanding of the universe and our place within it. Initially, when scientists detected these distant worlds in the early 1990s, it opened up a realm of possibilities that challenged our previous ideas about planetary systems. No longer confined to our solar system, astronomers began to explore a variety of planetary environments, sizes, and orbits, revealing a diverse collection of worlds unlike any we had ever imagined. With over 5,000 confirmed exoplanets, their study challenges the traditional boundaries of exploration. Unlike our own celestial neighbors, these planets exist at staggering distances, some thousands of light-years away. The methods used to identify these distant planets, such as the transit and radial velocity techniques, push the limits of our observational capabilities. As technology advances, we are now able to measure the atmospheres of some of these exoplanets, searching for signs of life or conditions that could support it. This has profound implications for astrobiology and the understanding of life's potential across the cosmos. Moreover, the variety of exoplanets has upended previous notions about planetary formation and stability. Some of these planets orbit their stars at remarkably close distances, challenging the concept of a habitable zone that we have long held true for our solar system. This wide-ranging diversity suggests that the universe may be far more hospitable than we once believed, prompting new theories on how planets form and evolve. Understanding exoplanets not only enriches our knowledge of celestial mechanics, but also reminds us of the vast potential for undiscovered forms of life. As researchers continue to analyze exoplanets, the boundary of our exploration continues to expand. Each discovery leads to questions about the nature of planets across different star systems and pushes us to consider the implications for technology, philosophy, and the future of human exploration. The search for alien worlds is not just about finding new planets. It's about expanding the horizon of what we know, inviting us to ponder how we might someday interact with life forms that could exist beyond our home planet. The search for life on distant planets significantly expands our understanding of the cosmic scale. When astronomers identify potentially habitable planets, they are not merely cataloging distant worlds. They are redefining our sense of place in the universe. For centuries, Earth was considered a unique oasis of life in an otherwise barren cosmos. However, as we discover planets in the habitable zones of their stars, we begin to realize that life may not be a rare phenomenon confined to our little blue planet. When scientists examine exoplanets, planets that orbit stars outside our solar system, they consider several factors, such as the presence of water, the planet's atmosphere, and its distance from its host star. This research opens up a new frontier in our comprehension of life's potential diversity in the universe. With thousands of confirmed exoplanets, we are beginning to appreciate that our solar system is just one of countless cosmic neighborhoods, each potentially hosting life in various forms. Each discovery tells us more about the vastness of the cosmos and the myriad possibilities it holds. Moreover, this quest challenges us to rethink how we recognize life itself. Earth-based life requires specific conditions, but extraterrestrial life may thrive under different circumstances. The search for life pushes the boundaries of our imagination and scientific theories. It compels us to think creatively about what constitutes a living organism, thereby shaping our understanding of biology on a universal scale. This broader conceptualization of life could imply that many more worlds are possible habitats than previously thought. As we continue to explore the cosmos, the implications of finding even the simplest life forms on another planet would be profound. It would suggest that life is a fundamental feature of the universe, woven into its very fabric. Such a discovery would reverberate beyond science, influencing philosophy, culture, and our own conception of existence. The search for life on distant planets not only reshapes our understanding of the universe's scale, but also our own significance within it. The search for extraterrestrial intelligence, commonly known as SETI, has been a pioneering force in the quest to find signals from beyond our own cosmic neighborhood. While traditional astronomy focuses on the observable universe, SETI shifts the spotlight onto the possibility of intelligent life that may exist elsewhere. This involves the listening for radio waves and signals that might be transmitted from advanced civilizations in distant galaxies. SETI operates with the belief that if intelligent life exists, it may use similar technologies that we employ, generating signals that can be detected. The organization primarily employs radio telescopes to scan the skies, seeking out unusual patterns in electromagnetic radiation. This method is based on the premise that advanced societies could be transmitting deliberate signals, perhaps as a form of communication or simply as a byproduct of their technological activities. Beyond just scanning for obvious communications, SETI also pays attention to signals that might previously have been dismissed as noise. Their analyses are constantly evolving, incorporating advanced algorithms and machine learning to refine their searches in an ever-expanding universe. An interesting layer to SETI's contributions is its collaboration with various disciplines and projects across the globe. For example, initiatives like the Breakthrough Listen project increase the scale and intensity of the search, aiming to listen to 1 million stars in our galaxy and beyond. This collaborative spirit fosters a vibrant scientific community, all united in the wonder that we might not be alone in the universe. Their partnerships with universities and private organizations enhance technological development, allowing for more sophisticated methods of detection. SETI's work consistently poses profound philosophical questions. What would it mean for humanity if we were to detect a signal from an intelligent civilization? Would it redefine our understanding of life itself and our position in the cosmos? Challenges remain, notably the vast distances and the finite speed of light, which can limit our ability to receive signals from beyond observable regions. Yet, the ongoing quest sparks curiosity and hope, compelling us to explore the unknown and seek answers in a universe teeming with potential possibilities. As we journey towards the edge of the universe, we encounter an array of unresolved mysteries that challenge our understanding of cosmic phenomena. One key puzzle is the nature of dark energy, the elusive force that drives the accelerated expansion of the universe. Despite its significant presence, making up about 70% of the total energy density, we still do not fully grasp what it is or how it operates. This mystery not only shapes our universe's fate, but also invites questions about the fundamental laws of physics. Another intriguing enigma is the cosmic microwave background radiation, the faint glow left over from the Big Bang. This radiation holds invaluable clues about the early universe, yet there are inconsistencies in the temperature fluctuations that scientists struggle to reconcile. Different measurements yield varying results about the universe's expansion rate. This discrepancy, often referred to as the Hubble tension, suggests that our understanding of the cosmos may be incomplete, or that new physics may be at play, waiting to be discovered. Additionally, scientists are captivated by the mystery of cosmic inflation, a theory that posits a rapid expansion of the universe just after the Big Bang. While this concept provides a compelling explanation for the uniformity and flatness of the universe, the details of this process remain murky. Questions linger about what could have caused such a sudden and dramatic expansion and what mechanisms may have triggered it. Finally, the ultimate edge of the universe brings forth the question of cosmic boundaries. Is there a definitive end to the universe, or is it infinitely expanding? If it does have an edge, what lies beyond it? As we probe deeper into these unanswered questions, we realize that the universe, vast and marvelous, continues to guard its secrets, beckoning us to explore and unravel the mysteries woven into its fabric. Cosmic background radiation, the afterglow of the Big Bang, serves as a key piece of evidence for our understanding of the universe's early stages. This faint microwave radiation fills the entire cosmos and provides a snapshot of the infant universe, revealing its temperature fluctuations and density variations. However, anomalies in this radiation challenge our traditional perceptions about the universe's structure and boundaries, sparking debate among cosmologists. One of the most significant anomalies is the observed alignment of temperature variations that appears to defy random distribution. Certain regions of the cosmic background radiation show unusual patterns that suggest these areas may be influenced by factors beyond our conventional understanding of cosmic evolution. This unexpected alignment raises questions about the homogeneous nature of the universe, which is a cornerstone of the prevailing cosmological model known as the lambda cold dark matter model. Moreover, these anomalies hint at the possibility of other structures beyond our observable universe. This could include remnants from other universes or cosmic features that we have yet to identify. Such revelations suggest that our universe may be part of a much larger, more complex multiverse. If this notion holds true, it could redefine the very concept of boundaries as we perceive them, pushing the limits of our scientific inquiry and imagination. Consequently, the implications of these anomalies extend far beyond simple temperature fluctuations. They compel us to reconsider our models, explore new theories, and ultimately seek a deeper understanding of how the cosmos is organized and possibly its underlying rules. The journey to unravel these mysteries is not just about the data collected, it is about expanding the horizons of human knowledge and curiosity about the universe we inhabit. The discovery of the Great Wall and other large-scale structures in the cosmos opens up fascinating discussions about the very structure of our universe. Astronomers have identified vast formations such as galactic walls, filaments, and clusters, which serve as some of the largest known structures in the universe. Among these, superclusters like the Sloan Great Wall stretch across hundreds of millions of light-years, representing the largest organized structures we can observe. These colossal formations are not merely impressive in size, they also reveal crucial insights about the overall distribution of matter in the universe. The presence of these gigantic structures indicates that matter is not uniformly spread across the cosmos. Instead, matter congregates in regions that can form walls, sheets, and filaments, with vast voids existing between them. This understanding directly impacts our knowledge of cosmic evolution and the fundamental forces that shape our universe. Additionally, the presence of these structures hints at the interplay between gravity and dark energy. As galaxies and matter clump together under gravitational influence, dark energy's expansion of the universe works against this pull. The balance of these forces ultimately shapes the large-scale structure of the universe. Understanding the formation of these superstructures offers clues about how galaxies evolve over cosmic timescales and how they influence each other. Finally, as we delve into the limits of the universe, these discoveries challenge our understanding of what lies beyond our observable horizon. The structures we see may only be a fraction of what exists, suggesting that the universe could be even larger and more complex than we can currently fathom. The Great Wall and its ilk are not just geographical markers in space. They are vital pieces of a cosmic puzzle, elucidating the vast and intricate framework of the universe itself. Cosmic voids are vast regions in the universe that contain very few galaxies. They are surrounded by denser areas filled with galaxies and clusters, creating a cosmic web-like structure. Understanding these voids is crucial for cosmologists as they provide insights into the overall structure and dynamics of the universe. These seemingly empty stretches of space hold clues about how the universe evolved and its current layout. Researchers have proposed that these voids could play a significant role in theories regarding the universe's edge or boundaries. With their immense size, cosmic voids can influence the motion of galaxies, affecting how they cluster and providing information about gravity's impact on cosmic expansion. The presence of these voids hints at the non-homogeneous nature of the universe, suggesting that not all parts of it are equally dense or active. This uneven distribution can help determine whether the universe has a definite edge or if it extends indefinitely. Further explorations of voids lead to fascinating questions about cosmic background radiation and dark energy. Since voids are relatively empty, they allow for a clearer view of the cosmic microwave background, the afterglow of the Big Bang. By studying how these voids interact with the cosmic background, scientists can refine their models of the universe's expansion and the forces at play. Insights gleaned from these observations can influence our understanding of the universe's fate and whether it will continue to expand forever or eventually contract. Ultimately, cosmic voids highlight the complex tapestry of the universe and the interplay of forces that govern it. By studying these vast, empty regions, scientists gain a clearer perspective on the larger cosmic structure, challenging us to consider the implications of a universe that may not have a defined edge, but rather a vast and intricate expanse that continues to surprise us. Cosmic rays are high-energy particles that originate from sources beyond Earth, such as supernovae and active galactic nuclei. When these particles travel through space and enter our atmosphere, they can produce secondary particles that create showers detectable by scientific instruments. By studying these cosmic rays, researchers can gain insights into some of the most extreme environments in the universe, even those that we cannot directly observe. One of the most intriguing aspects of cosmic rays is their ability to carry information about their origins. For instance, because cosmic rays travel vast distances, they can act as messengers from energetic events that occurred billions of light-years away. By analyzing the composition and energy of these particles, scientists can infer details about the environments from which they came. This includes information about magnetic fields, radiation levels, and the presence of various elements, allowing us to understand the processes that govern cosmic phenomena. Moreover, cosmic rays can help illuminate the mysteries of dark matter and dark energy, which together make up a vast majority of the universe. For some time, scientists have speculated about the role cosmic rays might play in understanding these elusive substances. High-energy cosmic rays may interact with dark matter, producing detectable signals that can be studied for clues about its nature and effects on the cosmos. This means that cosmic rays could hold pieces of the puzzle to explain what lies beyond the observable universe. Cosmic rays are far more than just particles zooming through space. They are intriguing time capsules that give us snapshots of distant cosmic environments and events, enriching our understanding of the universe's fabric. Each observation helps us probe areas that would otherwise remain hidden, reminding us of the vastness and complexity of the cosmos. Through cosmic rays, we continue to uncover the secrets of the universe layer by layer, expanding our knowledge of its most enigmatic elements. Quasars, or quasi-stellar objects, are some of the brightest and most energetic phenomena in the universe, offering remarkable insights into the distant cosmos. Formed from supermassive black holes located at the centers of galaxies, quasars shine brightly as they consume surrounding gas and dust. This process generates enormous amounts of energy, outshining entire galaxies and emitting radiation across the electromagnetic spectrum, from radio waves to X-rays. Because of their incredible luminosity, quasars serve as beacons, allowing astronomers to probe the universe's distant past. One of the primary mysteries revealed by quasars is the nature of the early universe. Observing these distant objects lets scientists look back in time, often billions of years, to when the universe was still in its infancy. Some quasars we see today formed when the universe was less than 1 billion years old, providing crucial information about the conditions that prevailed during cosmic evolution. Their existence implies that supermassive black holes grew rapidly in the early universe, raising questions about how they accumulated such massive amounts of matter in such a short time. Quasars also highlight the relationship between galaxies and their central black holes. The energy output of a quasar can influence its host galaxy, regulating star formation and shaping the galaxy's evolution. This interaction implies that the growth of supermassive black holes and the galaxies themselves are intertwined processes. By studying quasars, astronomers seek to understand the mechanisms at play in this relationship, offering a clearer picture of how galaxies evolve over cosmic time. Moreover, the light from distant quasars can provide critical information regarding the composition of the universe. As their light travels across vast distances, it interacts with intervening gas clouds, absorbing specific wavelengths. Analyzing these absorption lines unveils details about the elements present in the universe, offering insights into its chemical evolution. As scientists continue to study quasars, they reveal not just the mysteries of specific objects, but also the broader narrative of cosmic history, enriching our understanding of the universe and our place within it. Throughout history, humanity has crafted models of the cosmos that reflect both our understanding and our imagination. Ancient cultures, such as the Greeks and the Babylonians, envisioned the universe as a domed structure, with Earth at its center, surrounded by stars that provided a sense of completeness. These early models, though not scientifically accurate, laid the groundwork for our quest to understand the universe's vastness and boundaries. The transition from geocentrism to heliocentrism marked a significant turning point. In the 16th century, figures like Nicholas Copernicus challenged long-held beliefs by proposing that the Sun, not the Earth, lay at the center of our solar system. This shift opened the door to exploring the cosmos in new ways and began to loosen the grip of the idea that the universe had definitive edges. As we advanced into the age of telescopes, powerful tools like those developed by Galileo and Tycho Brahe allowed for a broader view, enticing thinkers to ponder not just the structure of our solar system, but the galaxy and ultimately the universe. By the 20th century, the development of the Big Bang theory shifted our understanding significantly. This revolutionary idea proposed that the universe began as an incomprehensibly hot and dense state, expanding and cooling over billions of years. This narrative of continual expansion led scientists to reconsider the boundaries of the universe. Rather than being a confined space with clear edges, the universe appeared to be an ever-expanding entity, creating questions about whether it might be infinite or if it had some form of edge. Today, these historical models inform modern cosmological theories. The pursuit to determine the universe's edges examines concepts like cosmic inflation and dark energy, which drive the universe's expansion and influence its ultimate shape. As scientists gather more data through telescopes and investigate the cosmic microwave background radiation, our understanding continues to evolve. The interplay between historical perspectives and modern scientific exploration demonstrates that our perception of the universe is an ongoing journey, one that reflects both our past inquiries and our current quests for knowledge. The Copernican revolution marked a pivotal shift in our understanding of the cosmos, fundamentally altering humanity's perspective of its place in the universe. Prior to this movement, the geocentric model dominated, which posited that the Earth was the center of the universe, and all celestial bodies, including the sun and stars, revolved around it. This view was widely accepted due to its alignment with everyday observations and philosophical notions of humanity's central importance in the cosmos. When Nicholas Copernicus introduced his heliocentric model in the early 16th century, he proposed that the Sun, rather than the Earth, occupied the center of the universe. This radical idea not only challenged existing beliefs, but also simplified the apparent motion of planets, explaining retrograde motion and the seasons with greater clarity. This shift was profound. It liberated astronomy from a system laden with complex epicycles and gave rise to a more elegant understanding of celestial mechanics. The effects of this revolution weren't confined to astronomy alone. The heliocentric model paved the way for subsequent thinkers such as Johannes Kepler and Galileo Galilei, who built on Copernicus's work and provided evidence that further supported the sun-centered system. This period stimulated a deeper inquisitiveness about the cosmos, leading to the eventual formulation of the laws of planetary motion and the invention of the telescope, which revealed an array of celestial wonders that were previously invisible. Additionally, the Copernican revolution ignited a shift in philosophical thought about humanity's role in the universe. As individuals began to grasp the vastness of space and complexity of celestial movements, they moved from a place of centrality to one of insignificance within a much larger cosmic framework. This transition set the stage for the scientific revolution, encouraging a reliance on observation and reason, and laying the foundational principles that would eventually lead to modern science as we know it today. The shift from a geocentric to a heliocentric model of the universe marked one of the most transformative moments in the history of science. For centuries, the geocentric model, which placed the Earth at the center of the universe, dominated intellectual thought. This perspective not only aligned with common experience, seeing the sun, stars, and planets move across the sky, but also reinforced theological views that placed humanity at the heart of creation. The cosmos was seen as a hierarchical structure with Earth, and by extension, humanity, occupying the most significant position. However, in the 16th century, astronomers like Nicholas Copernicus began to challenge this long-held belief. Copernicus proposed that the Sun, rather than the Earth, was at the center of the universe, leading to a fundamental rethinking of humanity's place in the cosmos. This heliocentric model did not merely adjust celestial mechanics, it initiated a profound philosophical and existential re-evaluation. If Earth was not the center, what did that mean for humanity's purpose and significance in the grand scheme of the universe? The work of later astronomers like Johannes Kepler and Galileo Galilei further solidified this paradigm shift. Kepler's laws of planetary motion demonstrated that planets moved in ellipses around the Sun, challenging the idea of circular perfection. Meanwhile, Galileo's use of the telescope revealed moons orbiting Jupiter, providing concrete evidence that not everything revolved around the Earth. This wealth of evidence forced society to reconsider the nature of reality and our understanding of the universe. As a result, the heliocentric model spurred the scientific revolution, emphasizing observation, experimentation, and critical thinking. It reshaped not only scientific inquiry, but also instigated broader cultural changes, laying groundwork for modern science. This monumental shift invited humanity to see itself as part of a vast, dynamic universe, fundamentally altering our perception and inspiring countless generations to explore the mysteries of the cosmos. Ancient astronomical observations lay the groundwork for modern cosmology, revealing humanity's enduring fascination with the cosmos. Civilizations such as the Babylonians, Egyptians, and Greeks meticulously tracked celestial bodies, using their observations to create calendars and guide agricultural practices. These early efforts not only deepened our understanding of the movements of the sun, moon, and stars, but also planted the seeds for more complex theories about the universe's structure and behavior. One of the most significant contributions from ancient civilizations was the geocentric model, which posited that the Earth was the center of the universe. While this model was eventually overturned, it initiated rigorous debate and inquiry that eventually led to the heliocentric model proposed by Copernicus. This shift drastically changed our understanding of our place in the cosmos. The impressive precision of these early measurements continues to resonate as they inform current technologies like satellite navigation and improve our understanding of stellar dynamics. Lastly, insights from ancient cultures about celestial phenomena often incorporated spiritual and philosophical dimensions, giving rise to narratives that resonate with human experience. These concepts remind us that humanity's quest for knowledge about the universe is intertwined with our search for meaning. By studying ancient astronomical observations, we find not only the origins of our scientific endeavors, but also a reminder of our shared wonder and curiosity about the cosmos, which continues to inspire contemporary cosmological theories. Aristotle and Ptolemy were two pivotal figures in ancient science whose ideas form the groundwork for centuries of astronomical thought. Aristotle, living in the 4th century BCE, made significant contributions to natural philosophy and physics. He proposed a geocentric model of the universe, placing Earth at its center, surrounded by 9 celestial spheres. This model suggested that the heavenly bodies moved in perfect circles, reflecting Aristotle's belief in the perfection of the heavens. His ideas influenced not just astronomy, but also philosophy, biology, and physics, establishing a framework that would dominate Western thought for nearly 2 millennia. Following Aristotle, the 2nd century astronomer Ptolemy advanced this geocentric view with a more detailed system. In his seminal work, The Almagest, Ptolemy introduced the concept of epicycles, which described how planets moved in small circles while orbiting Earth in larger circles. This refinement allowed Ptolemy to explain the observed retrograde motion of planets, where they appear to reverse their direction in the sky. His model was so successful that it remained unchallenged until the dawn of the Copernican revolution in the 16th century. Both Aristotle and Ptolemy emphasized empirical observation, even though their conclusions were flawed by modern standards. The persistence and acceptance of their ideas reflected the cultural and philosophical climate of their times. These ideas were codified through meticulous observations and detailed writings, leading to their acceptance by scholars throughout the Middle Ages and into the Renaissance. Their influence extended beyond astronomy, permeating various aspects of science and philosophy, often intertwining spiritual beliefs with empirical inquiry. This geocentric view left a lasting legacy, providing a framework for future thinkers. It wasn't until Nicholas Copernicus proposed a heliocentric model, suggesting that the Sun, not the Earth, was at the center of the universe, that the long-held beliefs of Aristotle and Ptolemy began to unravel. Understanding their roles offers insight into how scientific thought evolved over time, highlighting the gradual shift from philosophical reasoning to a more empirical, observational approach to understanding the cosmos. Artists and illustrators play a crucial role in enhancing our understanding of the universe's edge through their capacity to visualize complex scientific concepts. The vastness of space often defies our ability to comprehend it fully, but artists help bridge that gap by creating illustrations that make the abstract tangible. Through their work, they can depict cosmic phenomena like supernovae, black holes, and even the cosmic microwave background, allowing science to resonate on an emotional level. These visuals not only make complex ideas more accessible, but also inspire curiosity and wonder. For example, when artists render the cosmic landscape, they often infuse humor, drama, or beauty into their representations. This can motivate a broader audience, including those who might not typically engage with scientific literature, to explore and learn about the universe. Illustrations can catch the eye and spark conversations, encouraging people to ask, "What is out there beyond the edge of our night sky?" Moreover, artists collaborate with scientists to ensure that their representations remain rooted in scientific accuracy while still being visually engaging. These partnerships yield artwork that is both informative and imaginative. The ability to take scientific data, like the latest observations from powerful telescopes, and transform it into compelling images helps to communicate ideas about the universe that would otherwise remain abstract. This interplay of science and art underscores the importance of visualization as a tool for education and inspiration. Artists and illustrators serve as translators of the cosmos, rendering its mysteries into forms we can appreciate and understand. Their work encourages us to expand our horizons, inviting us to ponder our place in the universe while simultaneously feeding our natural desire to explore the great unknown that lies just beyond our reach. Filmmakers grappling with the task of depicting the universe's vastness encounter a unique set of challenges. One of the primary hurdles is the sheer scale of space. The universe spans an unfathomable distance, with galaxies millions of light-years apart. Translating that immense scale into a visual medium requires creative solutions and often involves compressing time and distance into manageable segments. It is a constant balancing act to convey both the grandeur of the cosmos and the limitations of human perception. Another significant challenge lies in representing the spatial dimensions and phenomena that are not directly observable. For instance, concepts like dark matter and dark energy play crucial roles in our understanding of the universe's structure but remain invisible to the naked eye. Filmmakers often rely on computer-generated imagery and scientific visualization techniques to conceptualize these abstract components. This artistic interpretation must remain rooted in scientific accuracy while engaging the audience's imagination, making the challenge even more complex. Additionally, filmmakers must navigate the tension between entertainment and education. Audiences often respond to dramatic narratives and visually stunning graphics, yet there is a responsibility to present factual information accurately. Striking this balance becomes critical, as misrepresentations can lead to misunderstandings of key scientific concepts. Filmmakers frequently consult with scientists to ensure the integrity of their portrayals, yet the need for artistic flair can occasionally lead to oversimplification or sensationalism. Finally, the concept of time is another intricate factor. The universe not only expands over vast distances, but also over immense stretches of time. Events such as the birth and death of stars or the formation of galaxies occur over millions or even billions of years. Translating this concept into a compelling story for audiences can be tricky, as the human experience is fundamentally grounded in a much shorter timeline. To convey these cosmic tales effectively, filmmakers often devise creative narratives that allow viewers to grasp the profound nature of cosmic events while anchoring them in relatable, human terms. Visual metaphors play a significant role in helping the public understand complex theories about the universe's edge. These metaphors transform abstract concepts into concrete images that can be more easily grasped. For instance, when scientists describe the universe as a balloon expanding, the idea becomes more relatable. The visual of a balloon inflating provides a simple way to picture how galaxies move away from each other as the universe itself grows. Furthermore, visual metaphors engage our imagination, allowing listeners to visualize spatial relationships and dynamics that are otherwise difficult to comprehend. Describing the edge of the universe as a vast ocean, for example, can evoke images of waves and horizons, prompting thoughts about the unknown and uncharted. This is essential when discussing topics like the observable universe versus what lies beyond, as it helps bridge the gap between scientific thought and everyday experiences. Additionally, these metaphors can evoke emotions and personal connections, fostering a deeper interest in the subject. When people understand astrophysics through relatable images, they are more likely to feel that the universe is not just a cold expanse of space, but a place rich with possibilities. This storytelling aspect enhances the learning experience, making complex theories accessible and intriguing, consequently sparking curiosity to learn more. In a world driven by visuals, particularly in the age of social media, these metaphors also make learning more shareable. Engaging images and concepts are likely to spread, allowing communities to discuss and explore these scientific ideas collectively. By wrapping abstract theories in the warmth of familiar visuals, we invite everyone to ponder the immense complexities of our universe while igniting a passion for exploration and discovery. Science museums and planetariums serve as essential gateways to understanding the vast and complex universe. These institutions create immersive educational experiences that make difficult concepts more accessible to the public. Through interactive exhibits, visitors can engage with the fundamental principles of astrophysics and cosmology, exploring everything from our solar system to the observable universe and beyond. This hands-on approach invites curiosity and encourages the pursuit of knowledge, allowing individuals to grasp the physical boundaries that limit our understanding of the cosmos. Planetariums, in particular, shine a light on celestial phenomena. With their state-of-the-art projection technology, they can simulate the night sky, transport visitors to distant galaxies, and showcase astronomical events like meteor showers or eclipses. This captivating visual experience helps demystify concepts such as the speed of light and the vast distances between stars. By presenting complex theories in a visually engaging context, planetariums ignite wonder and spark interest in further studies of space and science. Moreover, these institutions often host lectures, workshops, and educational programs designed to deepen public understanding of the universe's boundaries. They bring together experts and enthusiasts, fostering a community dedicated to scientific inquiry and exploration. By blending entertainment with education, science museums and planetariums nurture a culture of curiosity, encouraging visitors to ask questions and think critically about the universe they inhabit. Finally, as centers of research and knowledge dissemination, these spaces play a pivotal role in inspiring future generations of scientists, engineers, and thinkers. By making the mysteries of the universe tangible, they not only promote scientific literacy, but also instill a sense of responsibility for our planet and the cosmos. In a world where science education is more important than ever, science museums and planetariums remain invaluable resources for expanding our understanding of the universe around us. Music has an enigmatic quality that often serves as a gateway to experiencing the vastness of the universe. Composers frequently draw inspiration from celestial themes, using sound to evoke the awe and mystery of space. The tonal shifts in a symphony, for instance, can mimic the expansive distances of galaxies or the silence found in the void between stars. Listeners are taken on a journey that parallels the exploration of cosmic landscapes, creating a sensory bridge between the abstract concept of the universe and the emotional resonances of music. Many contemporary composers intentionally incorporate elements from the natural world and concepts of astronomy into their works. Consider the compositions that simulate the rhythmic pulse of a pulsar or the gentle undulations of a nebula forming. These musical pieces invite listeners to reflect on the universe's grandeur while fostering a sense of connection to something far larger than themselves. The use of varying tempos and dynamics can echo the movement of celestial bodies, lending a physicality to the sounds that resonates with our own experiences of time and distance. Notably, the harmonics and frequencies found in music may even resonate with the actual vibrations of celestial objects. Some scientists have analyzed the sounds of black holes and other astronomical phenomena, translating them into music that can be both beautiful and haunting. This overlap between the scientific and artistic realms deepens our understanding of the cosmos, as music becomes a medium through which complex astrophysical concepts can be articulated and felt. Ultimately, the interplay between music composition and interpretations of the universe's vastness reminds us that art and science are intertwined. Music can serve as a powerful reflection of our place within the cosmos, illustrating themes of isolation and interconnectedness. As we listen to these compositions, we are often led to ponder significant questions about existence, drawing parallels between our emotional journey and the infinite expanse that stretches beyond our world. In the realm of speculative physics, the very concept of the universe's edges challenges our traditional understanding of cosmology. Most of us envision the universe as an expansive and boundless entity, but what if it indeed has edges? These questions lead us into a fascinating area of inquiry where unconventional theories offer alternative views of our cosmos. One such theory is the concept of a toroidal or donut-shaped universe. In this model, space is curved in such a way that if you travel far enough in one direction, you'd eventually return to your starting point. This challenges the notion of edges entirely, suggesting a universe that loops back on itself. Amazing as it sounds, this toroidal universe offers an intriguing solution to the question of what lies beyond the observable universe. Perhaps nothing at all, as every path leads back where it began. Then, there's the idea of a multiverse, positing that our universe is just one of many, each possibly containing different physical laws and dimensions. In this theory, edges don't apply to our universe, but rather to the boundaries separating it from various other universes. Some interpretations suggest these multiple realms exist in a vast higher dimensional space, where dimensions beyond the familiar three contribute to the fabric of reality. Lastly, another speculative idea emerges from the field of cosmic inflation, which suggests that the early universe underwent rapid expansion. This could create bubble universes, where some areas expand while others remain compact. Depending on the dynamics of these inflating regions, what we perceive as an edge might simply be the limit of our current observable horizon, with much more existing beyond that we may never detect. Each of these theories invites us to reconsider boundaries and edges in a universe that constantly evolves, sparking our curiosity about the fundamental nature of reality. The concept of time travel captivates our imagination and poses profound questions about the nature of the universe. Traditionally, we perceive time as a one-way street, where events unfold in a linear fashion from past to future. However, if time travel were possible, it would challenge this conventional view and suggest that the universe does not adhere to strict boundaries. Instead, it could open up a realm of possibilities where the past, present, and future coexist in non-linear ways. Consider the implications of traveling back in time. This action raises questions about causality, the principle that cause precedes effect. If an individual could alter a significant event in the past, it could create paradoxes, like the famous grandfather paradox, where the actions of a time traveler might prevent their own existence. These paradoxes highlight that the timeline of events is not as fixed as we once thought, and may suggest the existence of multiple realities or timelines, effectively expanding our understanding of the universe beyond its conventional limits. Moreover, various theories in physics, such as the multiverse theory, explore the possibility of infinite universes existing simultaneously. This perspective posits that for every decision made, another universe branches off, leading to endless outcomes and scenarios. If time travel were possible, it could allow individuals to explore these alternate timelines, further blurring the lines that traditionally define our universe. Ultimately, the implications of time travel remind us that our understanding of reality is continually evolving. The interplay between time and space could mean that the universe is a far more complex, interconnected web than we currently envision. As we explore these ideas, we push the boundaries of science and philosophy, encouraging a broader exploration of what it means to exist within this vast cosmos. Thought experiments are powerful tools that scientists use to explore and expand theoretical frameworks about the universe. These mental exercises allow physicists to test principles and concepts without the constraints of physical experimentation. Instead of relying on tangible equipment or observations, they use their imagination and reasoning skills to envision scenarios and analyze outcomes. This approach is particularly significant in fields like cosmology and theoretical physics, where empirical data can be difficult to gather. Consider, for instance, Albert Einstein's thought experiments that contributed to his development of the theory of relativity. By imagining scenarios involving light in motion, he was able to question the conventional understanding of space and time. In doing so, he discovered that the speed of light is constant and that time is relative, depending on the observer's speed. Such conceptual explorations lead to groundbreaking insights that shape our understanding of the universe's limits, suggesting that our perceptions of reality may not be as straightforward as they appear. Moreover, thought experiments enable scientists to grapple with complex ideas that defy intuition. The famous Schrödinger's cat scenario invites us into the realm of quantum mechanics, illustrating the perplexing nature of superposition and observation in quantum states. Through this hypothetical situation, scientists can reflect on the implications of quantum theory, addressing fundamental questions about existence and reality. Thought experiments like these stimulate discussion and inspire further inquiry into the universe's vast mysteries. Ultimately, thought experiments play a crucial role in pushing the boundaries of human knowledge. They inspire scientists to think creatively and to formulate new theories that can later be tested through observation or experimentation. In a way, they are a necessary step in understanding the complex nature of the cosmos, encouraging us to consider possibilities beyond what is immediately observable and challenging the limits of what we know. The holographic principle is a fascinating concept that suggests our understanding of the universe might be entirely different from what we have long believed. This idea posits that all of the information contained within a volume of space can be represented as a two-dimensional surface. In other words, the three-dimensional world we experience could merely be a projection of information encoded on a distant two-dimensional boundary, much like a hologram. This principle gained traction through the study of black holes. When matter falls into a black hole, it seems to be lost forever, but researchers found that the information about that matter is not destroyed. Instead, it is theorized to be inscribed on the event horizon, which is the boundary beyond which nothing can escape the black hole's gravitational pull. This revelation challenges our classical ideas of physical boundaries, suggesting that what we perceive as solid and unyielding may, at a fundamental level, be more fluid and intertwined with the cosmos. If the holographic principle holds true, it calls into question not just our understanding of black holes, but the very fabric of reality itself. We might have to reevaluate how we think about space, time, and matter. Instead of being independent entities, these elements could be manifestations of deeper information residing at the boundaries of the universe. This rethinking could lead to revolutionary insights in fields like quantum mechanics and gravity, reshaping our fundamental understanding of the universe. Embracing the holographic principle means we are opening ourselves up to a richer, more interconnected view of the cosmos. Just as a hologram produces a three-dimensional image from a two-dimensional surface, our reality could emerge from deeper information residing beyond what we can see or detect. This profound realization could unify disparate areas of physics, ultimately leading to a more holistic understanding of how the universe operates and our place within it. Explorations of hypothetical constructs like Dyson spheres profoundly impact our perceptions of cosmic limits. A Dyson sphere, conceptualized by the theoretical physicist Freeman Dyson in the 1960s, is an enormous structure that could theoretically encompass a star to capture its energy output. This idea pushes the boundaries of what we consider possible in terms of energy consumption and technological advancement, stirring the imagination about the capabilities of advanced civilizations. This notion challenges our understanding of civilization development. It suggests that once a society reaches a certain level of technological sophistication, it would seek to harness energy on a star scale rather than relying on dwindling resources like fossil fuels. As we contemplate such constructs, we begin to question what we once thought was the pinnacle of engineering and resource management, prompting thoughts about our own technological future. Moreover, the idea of Dyson spheres forces us to confront the limits of the observable universe and the existence of extraterrestrial life. If advanced civilizations can create such structures, it raises intriguing questions about the distribution of intelligent life across the cosmos. Are we alone if these constructs are feasible? If civilizations thrive to the extent of building Dyson spheres, where are they? This line of questioning expands our perception of cosmic limits, suggesting that the universe, abundant and vast, has more potential for life than we may initially consider. The exploration of innovative concepts like Dyson spheres not only sparks the imagination, but also significantly broadens the horizon of our understanding of civilization and energy. As we ponder these tremendous possibilities, we find ourselves not only dreaming about the universe, but also contemplating our role in it and the potential futures that lie ahead. As we delve into the mysteries of the cosmos, the concept of the universe's edge has long captivated scientists and thinkers alike. Traditionally, many have envisioned the universe as a vast expanse with a distinct boundary. However, advances in cosmological theories are challenging this perception. Future theories may suggest that the universe is not only infinite, but perhaps also unbounded, meaning it could curve back on itself like the surface of a sphere. This would imply that if one could travel far enough in a straight line, they might eventually return to their starting point, negating the idea of a definitive edge. The introduction of concepts like the multiverse further complicates our understanding. If our universe is just one of potentially infinite others, then notions of edges become even more abstract. Instead of a singular cosmic boundary, we may be led to think of our universe as part of a much larger fabric of existence, interconnected with other realms that abide by different physical laws. Such theories could profoundly alter our perspective on where we stand in the grand cosmic scene. Moreover, future advancements in technology and observational methods may reveal phenomena that defy current understanding. For example, anomalies in cosmic microwave background radiation or unexpected gravitational effects could provide insights that reshape our view of the universe's structure. These discoveries might hint at hidden dimensions or layers of reality that exist beyond our current perception, further suggesting that the edge of the universe is not just a physical boundary, but a conceptual one. As we continue to explore and theorize, our understanding of the universe's edge is likely to evolve significantly. Enlightened by scientific inquiry, we could find that the universe is a far more intricate and expansive entity than previously imagined, nudging us closer to a deeper understanding of our place in the cosmos. Each new theory serves as a reminder that the mysteries of the universe are far from resolved, and that our quest for knowledge will lead us to even greater wonders. As researchers delve deeper into the cosmos, a myriad of intriguing questions about the universe's boundaries continues to elude definitive answers. One of the most pressing is whether the universe is finite or infinite. If it is finite, does it have an edge or boundary? This notion of a universal edge challenges our traditional views of space. The idea that there could be a point beyond which nothing exists, or that the universe might fold back onto itself, extends our imagination but remains a tantalizing mystery. Another key question centers around the rate of expansion of the universe. The discovery that galaxies are moving away from us and that this movement is accelerating has led scientists to explore the nature of dark energy, the force believed to drive this acceleration. What exactly is dark energy? Understanding this elusive component is crucial as it shapes not just the universe's current state, but its ultimate fate. The implications of dark energy stretch our understanding of fundamental physics and challenge us to rethink the mechanics governing cosmic behavior. Additionally, the concept of the observable universe raises its own questions. We can only see a portion of the universe due to the finite speed of light and the age of the universe itself. Beyond what we can observe, what lies in the vast unknown? Are there regions of space filled with matter that we cannot see? Or could there even be entirely separate universes, each with different laws of physics? These inquiries linger at the forefront of modern cosmology, pushing the boundaries of what we think we know about reality. Lastly, the structure of the universe also poses questions about the cosmic microwave background radiation, the faint afterglow of the Big Bang. What does the slight unevenness in this radiation tell us about the early universe? Unraveling these mysteries could lead to a deeper understanding of cosmic inflation and how the universe evolved from a compact point to the vast expanses we observe today. As scientists strive to answer these fundamental questions, each new insight opens the door to further intrigue, continuously expanding our grasp of the universe's enigmatic nature. The next generation of telescopes promises to revolutionize our understanding of the universe's edge, an area that has long intrigued astronomers and cosmologists alike. With advanced technologies and innovative designs, these telescopes will be equipped to observe celestial objects and phenomena that were previously beyond our reach. Notably, many of these new instruments are designed to peer deeper into the cosmos than ever before, providing a clearer view of the faint light emitted by distant galaxies and quasars. One key feature found in these sophisticated telescopes is their ability to capture images across multiple wavelengths of light, including infrared and ultraviolet. While visible light gives us a glimpse of the universe, other wavelengths can reveal a wealth of information hidden from our eyes. For instance, many early galaxies can only be detected in infrared, emerging from the cosmic fog that once surrounded them. By focusing on these wavelengths, scientists can study the formation and evolution of galaxies, better understanding how the universe expanded and evolved over billions of years. Moreover, upcoming telescopes like the James Webb Space Telescope are specifically designed to observe the universe's edge. This means observing distant regions of space that shine with light from stars and galaxies formed soon after the Big Bang. By analyzing this light, astronomers can gain insights into the very early universe, potentially revealing the nature of dark matter and dark energy, which remain some of the biggest mysteries in modern astrophysics. As these new instruments come online, they will not only enhance our understanding of the universe's history, but also refine our models of cosmic expansion. The discoveries made using these advanced telescopes could pave the way for fundamentally new theories about how the universe works, reshaping our vision of the cosmos as we unravel the mysteries hidden at its edge. The journey to the frontier of the universe is just beginning, and the next generation of telescopes is set to lead the way. The quest to understand the universe and its elusive limits propels researchers into various thrilling domains of study. One of the most promising areas lies in theoretical physics, particularly the field of quantum gravity. Scientists are working to reconcile the principles of quantum mechanics with general relativity. This groundbreaking integration could unveil insights about black holes and the nature of spacetime itself, potentially allowing us to explore what lies beyond the observable universe. Another frontier that captivates researchers is dark matter and dark energy. Together, these mysterious components make up approximately 95% of the cosmos, yet remain largely invisible and undetectable by traditional means. The ongoing search for new particles, like weakly interacting massive particles, and experiments aimed at measuring the effects of dark energy could fundamentally reshape our understanding of the universe's expansion and overall structure. Any breakthroughs in this area could provide unprecedented clarity on the ultimate fate of the universe. Astrobiology is also a fascinating field, as it investigates the possibility of life beyond Earth. As we explore the extremes of our solar system and beyond, scientists are discovering environments previously thought uninhabitable that might hold surprising forms of life. Missions to Mars, icy moons like Europa, and exoplanets in habitable zones are key to revealing whether we are alone in the universe or part of a more complex cosmic tapestry. Finally, advancements in technology, particularly in telescopes and observational instruments, are revolutionizing our ability to observe the universe. Next-generation observatories are being designed to detect gravitational waves and explore cosmic phenomena in unprecedented detail. As these discoveries unfold, they are likely to challenge our current understanding and usher in new paradigms about the universe's limits, potentially unearthing answers to some of humanity's most profound questions. Each of these research areas holds the potential to offer exciting breakthroughs and deepen our connection to the cosmos. Societal perspectives play a significant role in shaping the priorities of scientific research, particularly in the field of space exploration. Public interest can drive funding, attract talent, and influence the direction of projects. When communities become captivated by the prospect of exploring the cosmos, this enthusiasm translates into a powerful push for policy changes that can affect how research is funded. For instance, moon landings and the Mars rover missions captured the imaginations of millions. This public fascination not only inspired a new generation of scientists and engineers, but also prompted governments and private organizations to allocate resources accordingly. The more society expresses a desire for exploration, the more likely it is for governments to prioritize budgets that support ambitious missions. This dynamic creates a feedback loop where successful missions invigorate public interest, which in turn fuels further research. Moreover, societal values and concerns can channel the focus of space exploration into specific areas. Issues such as climate change, resource management, and life beyond Earth have become focal points due to public awareness. As communities express their worries about the environment or the sustainability of life on Earth, research priorities can shift to address these concerns, focusing on finding solutions through space technology. This can lead to the development of new technologies aimed at understanding our planet or searching for alternative habitable worlds. The interplay between societal interest and scientific research is vital. The public's curiosity and values can not only dictate the funding and attention given to specific projects, but can also encourage scientists to adapt their research to meet broader human needs. This synergy helps shape the future of science, creating avenues for exploration that resonate with the hopes and concerns of society as a whole.